So that's the point. So again, I'm preaching to the converted here. And the question is, what if this quantum channel corresponds to a memoryless continuous time evolution? Okay, so to analyze this, we imagine that like I'm going to go through this quantum channel, and I can divide this quantum channel into small time intervals dt, right? And the goal is to have a linear time evolution for each dt in which the state of the system after the next step only depends on the state of the system before the step. So this is the condition that we want to impose, but we still obviously want to describe each slab by some CP-TP map, right? So then obviously continuous means in the sense that like if I eventually take dt to 0 in the limit and this number of steps to infinity. So in this case, we obviously, if there is no environment, we still have to have Schrödinger equation in its format for the density operator, and I'm taking h bar equals to 1. Okay, just so that nobody misses an h bar here, and then the conditions that I want. So whatever is due to the channel, right? So the coupling to external degrees of freedom, I want it to come in this form, like it should be in first order in time and should depend only on rho of t. And it is easy to show that if I choose the operators of my CP-TP map in this format, like I choose each one of them and to be proportional to some operator acting on the system. And the proportionality constant is a square root of a small probability that's given by some rate times dt. And if I choose the one of them to be the one that guarantees me that the sum of all of them will be identity, if you keep to first order in dt, then the sum is equal to identity because the terms that show up are of the order of dt squared. And you end up with an equation for the evolution of your system that is in this form. And this is the Lindblad, Goritsky. I always forget the other names. Sudarshan and Kosakovsky. Thank you very much. Form, right? They derived it in separate papers in the same year. And so this is the overall equation. So this is the standard master equation in this form. It's Markovian. The Markovianity is implied here in this condition that like it rho of t plus dt only depends on rho of t. And this equation is not unique. In which sense? It is invariant under a general transformation of this type here. And this transformation works like this. If you line up these operators in a vector, what this transformation means is that I apply some unitary transformation to this vector, in which each entry is one of these operators here. And I can also add a constant, a complex number times identity. Okay. And if I do this, I will change this part of the equation to a new format like this, except that there will be an extra term that looks like a Hamiltonian. So it's a kind of Hamiltonian correction of this form, okay? And if if I make this transformation here, and I correct my Hamiltonian by this term, I get the same time evolution for my system. Okay. And I need you people to save this information. In particular, to save the information that like if alpha is 0, then this part is the same, and I just transform this non-unitary part of my evolution. Okay, just save this information for now. Okay, so then we go to quantum jumps and quantum trajectories in that sense, in the sense of the one that I want to approach here in my talk. So again, I have this time evolution, and I will call these operators my jump operators, and this operator will be my no jump operator. So now I'm talking about discrete time step evolution. So instead of having a continuous time evolution now, I'm discretizing time in small time steps dt. How small? These time steps, they have to be much smaller than 1 over the gamma rates, the rates at which I couple to my reservoir. Not couple, I mean the rates that my reservoir induce in the dynamics, but they still have to be much larger than what's called the correlation time of my reservoir. Okay, and the reason for this is that I actually that's a condition for me to get to the Lindblad equation from microscopic models. Okay, and otherwise, again, that's also something that's very interesting. I don't know if you guys know, but Markovian evolution is also an approximation. Okay, there's no such a thing as Markovian evolution. So there's no such a thing as isolated quantum system. There's no such a thing as Markovian evolution. Those are two approximations. Anyway, then quantum trajectories is a very nice way to solve my problem. Because usually if I'm dealing with a density operator, the dimension is very large, and I have to solve an equation of a very large, so I have to solve a very large number of equations. It grows with the square of the dimension of my Hilbert space. And but here, one way to solve this equation is actually to split it into trajectories. And trajectory means if I start with a pure state, in each time step, I can draw which one of these guys happen, either a no jump or one of the jumps with their proper probability. And depending on the number that I draw, I apply the corresponding operator. And so one trajectory would mean one realization of my dynamics, in which, so one trajectory is one branch of this tree here, okay? So let's say in the first time step, I draw a number that tells me to apply the no jump operator, then I come here, then I get jump 1, then I come here, then I get jump 2, then I come here. So this is one particular trajectory. And the way to recover so again, to each trajectory, I have the application, consecutive application of the operators corresponding to the jumps that I drew. And there is a probability of this happening, and this is given by this number here. And then how do I recover rho of t? What I do is that I take the projector of each one of the states corresponding to the trajectory, I multiply by the probability of that trajectory, and I sum everything. And so that's the quantum trajectories method. It's a very powerful computational method to solve the master equation, because now in each time step, I always have a pure state. So I'm always dealing only with a vector. So the dimension is much reduced. And obviously, the more complicated the equation, the more number of trajectories I need to take, and so on and so forth. But anyway, it's a powerful way to solve this equation. And okay. So one example of this, let's pick up spontaneous emission. Spontaneous emission, there is only one operator, which is sigma minus. So I'm talking about a qubit. So my qubit is in the excited state, it gets down. If it's in the ground state, it stays where it is, okay? And so there is only one jump. It's the one that brings my qubit down. The master equation in the already, I'm writing it already in the interaction picture. So I got rid of my Hamiltonian part. It's given by this, in this format. And the no jump is given by this operator. And these are the solutions. This one is easy to solve in time, obviously. And these are the solutions for my block sphere components. So, and with this, I can extract the map. I think you have seen this map before in this conference already. So this is the overall map. If I want to, so this is the map that gives me the CPT map for the solution at a given time t. And you see that if gamma t is much smaller than 1, then this map goes into the operators that I wrote right here. So this is consistent, of course, as it should be. So this is an example for spontaneous emission. And again, how to produce a map for dt. I can take my two-level atom, I can couple it to a leaky cavity, for example, in the vacuum. And in this way, if I start with this qubit here in this state, and my environment is in the vacuum, after a small amount of time, either nothing happens because my qubit in level 0 doesn't emit, or I have a probability of staying where it is, and I have a probability of emitting, and then there is one photon in my environment, and if I trace out the environment, I recover the map. So this is one way. So so far, I have explained to you quantum trajectories as a powerful mathematical computational way of solving the master equation, but there is actually a physical interpretation to it. And the physical interpretation is, let's say that this happens. Okay, let's say that I have a qubit and it can emit a photon, and somehow I can monitor if this photon is in the environment or not. Let's say I surround my qubit with a round detector, or I guide. That's easier to do. I guide my emission in a particular direction. We can discuss later how to do it. It's not that difficult nowadays. And I place a detector on outside my guide. And then my detector, I open my detector and ask, is there a click or there's not a click? If there isn't a click, then I apply the no jump. If there is a click, I apply the jump operator. So that's a physical way to implement quantum trajectories, for example, for spontaneous decay. Okay, so obviously, in this case, each single round, if I start with a pure state, I keep my state pure, and I have, so each realization is one trajectory and a physical realization of one trajectory. So far we have, so now we have a physical motivation, physical realization of trajectories. And so that's exactly what I have said. And then you get a probability, that's the probability of happening a jump, and the probability, no jump, and the probability of having a jump, okay? And then it's interesting to notice that, like, even if, in the case of a spontaneous emission, okay, even if there is no jump, the state of the system changes. And the reason is because, obviously, because 0 cannot emit and 1 can emit, if in a time dt I have no jump, this unbalances a little bit the previous population of 0 and 1 in my qubit. Another way to see it is that there is a probability that I keep monitoring and I get no jump. This probability, obviously, is modulo alpha modulo square, because it's the probability of having the system, finding the system in level 0. So the sequence of no jumps eventually has to collapse to the ground state of the qubit. Okay, that's another way of understanding why the no jump affects the state of the system anyway. So again, how to produce a trajectory. I have my system, I have the environment, I make a measurement in the environment, then I reset my environment and I do it again and again and again. Fine. So as I said, two remarks. One of them is that like the system, if I have a jump, the system now is in the ground state and it stays there. And if I have a no jump, then I have to correct the sequence. Okay, and so this I have covered already. Okay, so you see that like if I ask what is the purity of my system, if I don't monitor the environment, the system starts to decohere and eventually goes back to a pure state, obviously, because it's a spontaneous emission. The asymptotic state is the ground state, which is pure. But if I monitor, I have the system pure the whole time, if I monitor the environment. And if I look at in the block sphere, here I'm in a frame that is rotating with the frequency of the Bohr frequency of the system. Then if I don't monitor, my dynamics goes through the ball, and so it enters the inside the sphere, and I have this red trajectory here. And if I'm monitoring, while I have a no jump, I'm going through the sphere, and when I have a jump, then I jump straight to the ground state. Okay, so this is how I see the trajectory in the block sphere. So I'm gonna bring now an example of quantum jumps that was made in the lab in quantum optics. So this is a very nice work done by Serge Ross group in LKB in France. So here it's the roles are reverted. Actually, the quantum system is the field inside the cavity, and the atoms are gonna be my detector. Okay, and just to explain very quickly how it works. The atoms are produced in an oven. They are pumped into a Rydberg high circular Rydberg state here. They go through this cavity here, in which the cavity role is to pick up an atom that is in the ground state and prepare it in a superposition of ground and excited. Then they interact dispersively with the cavity field that I want to measure. And this dispersive interaction is in such a way, it's timed in such a way that if there is 0 photons in the cavity, the atom stays where it is. If there is 1 photon in the cavity, the atom rotates in the equator of the block sphere to the opposite side. It gains a phase, a minus phase between G and E. And to be more precise, we are talking odd and even here, but let's say 0 and 1 just for the sake of my argument here. And then this second cavity here rotates back the atom. So if the atom was, if there was 0 photon, the atom is rotated now to the excited state. If there is 1 photon, the atom is rotated back to the ground state. So now in D, you detect the atom and you can tell 0 or 1. Okay, so the atom is a detector for the field inside the cavity. But the cavity field is also coupled to its environment at a certain temperature. So the cavity field can lose photons to the environment and can gain photons from the environment. And you keep detecting them. And what you see, so basically, the evolution of the field inside the cavity is given by an equation of this type. This is the action of the thermal reservoir in the field. Okay, so this is decay and this is pump. And this is actually the action of the atoms if you don't detect them. So if you don't detect them, the atoms also work as a reservoir for the field inside the cavity, one that dephases the state of the field. But like now they are measuring the atoms, right? And what you are seeing here is like this. A bunch of atoms living in level G means that you are collapsing the field in 0 photons, and then eventually a thermal photon gets inside the cavity and you start collecting atoms in the E level. and then the thermophoto leaves the cavity, and you get back to collecting atoms in the G level. So here you got a jump. So here the state of the cavity state jumped from 0 to 1. Okay, that's a jump. We can discuss this later as well. There are many, many interesting features here regarding detectors, stuff that has been discussed in this conference regarding detectors, regarding quantum to classical transitions. You see that, for example, because they have large errors in determining the state of the atom, what they do is a majority vote. They collect many atoms in a sequence, and if many of them are in the same state, then they say that they are seeing now the state of the cavity in a given Fock state. And so this is, although each atom in principle is already a detector for the state of the cavity, to be clear, they need to collect many atoms. So this is again a discussion of how quantum detectors and classical detectors work, if you guys want to go into this direction. And here is a reconstruction of the master equation, the master equation evolution for the state in the cavity. So this is one trajectory. So this is the average over 5 trajectories. That's the average of 15 trajectories. That's the average of 904 trajectories. And you see that when you go to 904, you recover the traditional exponential decay for the excitation in the cavity that you should get for a cavity coupled to a thermal reservoir. Okay? Fine. So this is a quantum optical example. So now let's go to our, I asked you to remember that there were many different ways to write the same equation. Let's see what happens in this case. So let's explore a different type of reservoir. We're talking now about dephasing. For dephasing, my operator that acts on the system in the jump is sigma z, for example. This is the master equation. That's my jump operator. That's the no jumper operator. And if you look at here, you see that the no jumper operator is actually proportional to identity. Dephasing is what we call a unital map, right? And that means that if I monitor my reservoir and I get a jump, I apply sigma z to my system. If I monitor my reservoir and I don't get any jump, the state of the system stays where it is. It's the same state, right? And obviously, this is you have a similar behavior for any operator that defines the Bloch sphere. Obviously, because I mean they are similar by rotation, so there's no reason why sigma z should be better than any other of them. So it's the same for sigma x and y. Okay, so please save this information. And so, for example, if you have an entangled system of 2 qubits, dephasing leads to disentanglement. Dissipation leads to disentanglement. So if they are decaying, eventually the entanglement vanishes. And if there is noise, if there is temperature, actually you get more noise and you get a faster disentanglement. So this is the curve with temperature, without temperature, so spontaneous emission, and this is the curve for some temperature. You get a faster decay. Okay, so the master equation for decay with temperature is given by this. It's this equation that gives the evolution of a qubit under a thermal reservoir. So we have the term for decay and the term for absorption, incoherent absorption. There is a ratio between the rates, and the asymptotic state is given by this detailed balance equation here. And if you're monitoring the reservoir, now you have 2 jumps: the jump for spontaneous emission, the jump for incoherent absorption, and the no jump is given by this vector, this operator here. So this is, again, the quantum trajectories picture for a thermal reservoir, okay, of a given temperature. And there is a limit for this dynamics, which is given by infinite temperature. Infinite temperature can be understood in this sense as the average number of photons in my reservoir being much larger than 1. So the rates for decay and absorption become the same rate. The asymptotic state for this dynamics is the identity in my qubit. And if in this regime, you see that the no jump actually becomes proportional to identity, because now gamma minus is equal to gamma plus, and the no jump becomes proportional to identity. The jump happen at the same rate, but if you remember now that this is not unique, you're going to remember that like I can define new jump operators, which are linear combinations of the previous ones. And if I do this new jump operator is proportional to sigma x, and this new one is proportional to sigma y. So now, if I had a way to detect my jumps in this superposition, instead of detecting the clicks for emitting and absorbing, detecting superpositions of emission and absorption, okay, I actually would get unitary transformations to the state of my system instead of non-unitary ones. So this is quite interesting, and the question is, how can I do it? So to honor my good friend Gerardo that mentioned that I keep playing with my three-level scheme, okay? I'll bring back the three-level scheme that you guys have already heard. So I'm not going to spend too much time here, but the idea is that like if I have a three-level atom, and this is the spontaneous decay from E to G, and this is the spontaneous decay from I to E, and I pump from G to I with a coherent field. If gamma, large gamma, is much larger than big omega, which is the Rabi frequency here, then I can eliminate level I, and I end up with an effective thermal reservoir acting on my qubit, but one in which now I can learn both gamma minus and gamma plus. If I detect a photon of this type, I attribute gamma minus. If I detect a photon of AL type, I attribute gamma plus. Okay, so this is a way to build an artificial temperature for my qubit. So remember that now I am increasing noise. I'm adding noise to my dynamics, right? However, I'm adding noise in such a way that if I have a way to combine the detection of AL and AR, I actually can implement sigma x and sigma y as my jumps. So I can do this, for example, let's say that AL and AR are of the same frequency, but they have different polarization, orthogonal polarization. So now if I combine them in a polarized beam splitter, and I detect, let's say that this is circular polarization to the right and to the left. If I detect horizontal and vertical polarizations, if I get a click here, I don't know which one of these processes happened. I erase the information about which process happened, and I have to apply sigma x to my qubit. And if I detect a click here, I have to apply sigma y to my qubit. So this is actually a quantum optical way to implement these trajectories that in which for each jump, I have a unitary evolution in my system. And if I look at this, for example, let's say that I have these two qubits entangled, and they are decaying. They are spontaneously decaying. So I'm going to lose this entanglement. So now what I do is actually I pump them, each one of them locally, and I monitor the photons that are emitted by the system. Okay? So now I'm locally monitoring the photons that are emitted by the system, but each time I get a click, it's a local unitary operation acting on my qubit, and we all know that local unitary operations, they don't change the amount of entanglement of my system. So now I'm preserving entanglement by adding noise to the system, but measuring the effect of this noise in a smart way. Okay, so and because of the algebra for spin half, it's very easy. I keep getting the signals and each one of them corresponds to one unitary. And in the end, if I want to bring back to my original state, if I need to do it, I can just change the meaning of each state. But if I want to do it, I just need to apply a final local operation to my system, and I bring it back to the initial state. So in each realization of my dynamics, not only the state is pure, but entanglement is preserved. Okay, and here what we show is what happens if you have imperfect detections. So here is the spontaneous decay, so standard master equation solution for my dynamics. Here is the standard master equation solution with the added noise, with the optical pumping. And here, obviously, is the entanglement if I can monitor all the clicks perfectly. And here is what I get if I lose some clicks. So, if, for example, if my detection efficiency is 0.9, I still get much better than the master equation solution. Okay, so this is an example of a quantum optical way to actually locally protect entanglement from spontaneous emission. Okay, and because I still have some time, I want to give you another example. Okay, so this is actually a node work with a very bright student of mine, so here is an example of the power of using quantum trajectories to compute something, but also to understand what's going on in the physical problem. Okay, so if I asked you, I told you about these cavities here that rotate the atomic state. So they rotate the atomic state without entangling with it. So usually we would say that this is a laser field of very large number of average number of photons. That's how you think about unitary rotations of a qubit, of a two-level atom. Why? Because if it's a unitary rotation, it means that like I'm acting on my system from outside without entangling with it. So that's a semi-classical approximation. Every time I have two systems interacting, they are both quantum, and usually they will entangle. The semi-classical approximation is to say that like I can do this interaction, but this system has some property that it doesn't change that much, so it doesn't entangle with my quantum system. Okay. However, the average number of photons inside the cavities R1 and R2 is 1. It's a coherent state of average number of photons 1. So this should entangle with my atom while it is rotating it. It should. Why doesn't it? So if you talk to them, the explanation is, well, it's because this is a lossy cavity that is constantly pumped, and the photon doesn't stay long enough inside to entangle with the atom. But this is all said in words. Okay? So what I'm going to show you now is that we can use quantum jumps and quantum trajectories to actually see the mechanism of the photon changing the state of the atom, but not entangling with it that much. Each photon that goes through the cavity. So that's what I'm going to show you next. So so I'm describing the physics here of this R1 cavity. So the interaction Hamiltonian in the interaction picture is given by standard James Cummings Hamiltonian for the cavity field and the atom, plus an external drive to the cavity field. And then you have the component for the no jump given by the leakage of photons from this lossy cavity to the outside world. Okay, and the master equation is given by this term plus the standard master equation term. And again, a jump is a loss of a photon in the cavity. The no jump is given by this operator, And again, I have the Markovian CPTP method. Fine. So what we did is first we used quantum trajectories to numerically solve our problem. This is not an easy problem to solve, okay? And so we used quantum trajectories to solve the problem. We started with this state here because that's what happens. The atom is coming from outside and the state in the cavity is stable. This is the asymptotic state of pumping my cavity and having my cavity emit. Okay, it's a coherent state, and the average number of photons depend on the ratio of my pumping and my decay rate. And here, as I said, the average number of photons is 1, which means that gamma is equal to 2F. Okay? So you see that, like, if gamma is much smaller than G, the coupling between the atom and the field, that means that this is not a lossy cavity, it's actually it's a very good cavity. And what happens is that I have the blue dotted line here, and you see that this is the entropy of the cavity field. That's the fidelity of the cavity field with its initial state. This is the entropy of the atom, and you see that what you have is Rabi oscillations. Okay, you have Rabi oscillations. They are not going to be full Rabi oscillations because if alpha is of the order of 1, there is a large component of vacuum, and G0 doesn't evolve in time. But it's still Rabi oscillations. So what I'm plotting here is the global entropy of atom and cavity, entropy, cavity entropy, and fidelity of the cavity with the initial state. So we just need to focus on the dot blue line, which is Rabi oscillations, the limit of gamma much smaller than G, and the pink dash dot line, which is gamma much larger than G. So if you look at here, for gamma much larger than G, the state of the cavity remains the same all the time. The purity obviously remains the same all the time as well. So what's happening here is that in this limit, the state of the cavity is not being affected anymore by the presence of the atom. Okay? However, the state of the atom is going to change, as I'm going to show. But if you look here, you see that the global purity of the system and the purity of the state of the atom, they have the same behavior. So basically, the question is, with whom is the atom getting entangled to? Well, the atom is getting entangled with the reservoir. The atom is getting entangled with the photons that are leaking from the cavity. Okay, that's what's happening. So this is the regime of the Ramsey zone, the R1 cavity. The coupling with the atom is of the order, by that time of the order of 10 kilohertz, and the loss of the cavity of the order of 2 megahertz. So this ratio here is 200. 200? Yeah. So, okay. Again, I'm using quantum trajectories to solve my dynamics. So here what you guys see is if you follow the pink dotted line, dash dot line, that's the Bloch sphere. And basically what you are seeing is that the atom is undergoing a rotation. And up until this point, I can say that the rotation is at the sphere, and then it starts to get inside the ball. What it means is that obviously this unitary rotation of the atom has a limit. Okay, if I keep doing it, then I'm going to start losing purity of my atom, and they know this. So they know that the limit is a little bit higher than what they need. They need to be able to do what's called a pi over 2 rotation, which means bringing from G to the superposition of G plus E, or from this superposition to E or G. Okay, that's what they need, and they have exactly what they need. And here Well, so here again, what I'm plotting is the negativity of the atom field state, which means the entanglement between them. And you see that in the good cavity regime, they get highly entangled. In the bad cavity regime, they barely get entangled at all. Okay, so the atom is not getting entangled with the cavity. Okay, so now the question is, can I now, analyzing single trajectories, understand what they meant by the photon doesn't get, so the photon changes the atom, but doesn't get, but the field doesn't get entangled with it. So if I look at the no jump trajectory, then the no jump trajectory is given by this equation here. And if I have a small gamma, okay, this effective Hamiltonian, non-emission Hamiltonian, is dominated by this term here. And this is the Jaynes-Cummings, and then I get the oscillations that I should get. So basically, the no-jump trajectory will make Rabi oscillations between my atom and my field. And then if gamma is very small compared to G, for the time of 1 or half Rabi oscillation, the chance of having a jump is very small. So most of the time, what I get is the no jump trajectory. Okay. However, if I have large H, gamma, I'm sorry, then this is the term that dominates my no jump trajectory. Okay. And in this case, this term here, because F is of the order of gamma as well, so this term is very strong as well, this can be considered a perturbation of this Hamiltonian here. And if I treat this as a perturbation of this Hamiltonian, what I get actually is that this term will actually rotate my state in the Bloch sphere. So the no jump will rotate my state in the Bloch sphere. Okay? However, in this regime, obviously, because gamma is large, I get many jumps. So I need to take care of the jumps. I need to understand what's happening with the jumps. So I'm going to skip this slide. We can talk about this later. But like for large gamma, I can calculate in each trajectory, because the state of the whole system is pure, I can calculate the variation of entanglement of my system due to one jump. And I calculate the variation of entanglement due to one jump in this way. I calculate the entanglement of my state after the jump minus the entanglement of my state before the jump. And here what I'm showing you is the variation of my state, of the entanglement of my state for a jump as a function of gamma. And I'm picking up this t here. This t is chosen as the time in which the larger variation of entanglement happens due to a jump. We studied this before, so we know. So I'm getting the worst that can happen. Okay, and you see that like the entanglement between atom and cavity field because of a jump goes to the change of this entanglement goes to 0 as gamma gets larger. And here it's the calculation of the full variation of entanglement due to one trajectory. So this function here tells me if there is a jump, I assign 1. If there's no jump, I assign 0. So this is the full variation of entanglement due to jumps in one trajectory. Okay? And so just remember that like a jump, because I'm monitoring the cavity field leakage, a jump acts on the cavity field. It's an operator that acts on the cavity field. So it's local in the cavity field Hilbert space. And a local operation cannot create entanglement. It can destroy entanglement. It can enhance entanglement if there is entanglement present, but it cannot create entanglement out of nowhere. And if the cavity field remains in its pure state the whole time, the approximation is that the atom times the cavity field is separable the whole time. So it's reasonable that this jump does not create entanglement between them anymore. This is for the large gamma regime. So then I can average this quantity for all the trajectories, and what I'm showing here is this average. And you see that obviously for very small gamma, there is no jump, so there is no way that a jump can create entanglements. Then this increases, and then it decreases as time goes by for larger gamma. No, so not time, sorry, for larger gamma. So you see that jumps do not create much entanglement between the atom and the cavity, but they actually do help to drive the atomic state towards the excited state as well. So not only does the no jump trajectory guide my system through the Bloch sphere, but whenever I get a jump, I get an extra bump towards the state that I want. Why? Because G0 cannot produce jumps. So obviously, if I get a jump, I favor state 1 of the atom, okay? So that's all that I wanted to say. So with this, we translated into a physical, we gave a proper physical mathematical analysis of what people used to say about this Ramsey zone. They used to say it was like this, but they had never shown it. So here we used quantum trajectories to show it. And this is published in this paper with Eduardo Mascarenhas, who by that time, when he did this work, he was an undergrad student. So this is actually his scientific initiation program, okay? And that's I mean, he was a very bright student of mine. And he continued with me. We did lots of works. So with this, I am 1 minute late, but I want to thank you. And just before, I need to advertise Paraty, okay? That's a conference that we organize every 2 years in a very nice city in Rio, in the Rio state. It's a very nice conference. There are people here who have been there, and foreigners and nationals. And we are just about to open for registration. And please feel free to apply. So it consists of 2 parts. There is a school on quantum information. We already have basically the team of professors. It's a nice team as usual. And then there is a workshop in the next week, the following week. And the workshop, we don't have invited speakers for the workshop. Everybody applies, everybody sends their abstract. We select the works as talks or posters, and everybody is welcome to come. And we have limited space, so we can fit around 120 people more or less. But it's a very nice environment, and we organize the conference in such a way that you never get too tired. You have, for example, the school, you have talks in the morning, then a huge lunch break, then talks in the afternoon. The workshop in the same way, talks in the morning, huge. Instead of a conference dinner, we have a boat trip conference dinner if you want. So I mean, you should visit. You can ask Gerardo, for example, what he thinks about it. Okay, so thank you very much.
So questions? Thank you for your great talk. And if I understand it right, we can keep the purity and entanglement by observing quantum trajectory. So I think it can be applied to quantum error correction or quantum error mitigation. So do you have any idea or plan to do that by using your quantum trajectory?
Yeah, so thanks for the question. Actually, you can even do more than that. So you can by monitoring, you can keep your entanglements. You can do more than that. You can, for example, entangle qubits with it as well. So that's some other work that we did. So it's simple to understand. If each qubit now can emit or so can emit photons of the type gamma minus or gamma plus. And you now erase the information about which qubit emitted, so now you can entangle them as well. So basically, you can actually do not only preserve entanglement and protect entanglement and do error correction if you want, but you can actually entangle. You can have 2-qubit entangling gates. You can have local unitaries as well. So I mean, it is a powerful scheme. The caveat, obviously, is that you need very good detection efficiency.
So which means you can make the quantum gate by using the
Yes.
concentration.
Yes.
Okay,
Yes.
thank you.
So I was a bit skeptical when you said at the beginning that computing the single trajectories would be more efficient than computing the average density matrix, because I guess you have an exponential number of trajectories instead of one matrix that evolves. However, I think that single trajectories get a lot more information, as you showed, and I was wondering if they are getting popular lately because of measurement induced phase transition. I don't know if you ever heard of this, and I think it's very similar to what you did with the emergence of classicality. So you can say you did it before it was cool, and I don't know if these things can be related or if you have heard of them.
So just repeat they are similar to
Measurement induced phase transitions.
measurement induced phase transition.
So basically, you have a many body system that evolve through a random quantum circuit, and with some probability p, you measure one of the systems, let's say one of the qubits, and with high probability, when the probability is high enough, you have a phase transition in the entanglement entropy, and this phase transition is in the universality class of percolation.
Yeah, absolutely the same type of physics. Yeah.
Okay.
Same concept. Yeah, absolutely the same concept.
So they should cite you.
I get no, but it's okay. I don't care for this. I mean, it's interesting that this is one of the nicest things about physics, right? Is the fact that you come from a completely different angle, completely different way of thinking, and eventually you're actually talking about the same physics. This is beautiful. This is actually one of the things that I like the most about physics. So yeah, it's very, and it's nice that other communities rediscovered the wheel, but from a completely different angle. I like it actually, because usually both communities profit. So now, for example, I'm gonna take a look at this, and I'm gonna see what's happening in this many-body community and what they are doing, and maybe I learn lots of interesting things about it now. Thank you for your comment. Thank you very much.
Further questions?
I just want to give some comments about the phase-induced phase transitions, because phase kind of measurement in this phase transition is kind of pure state, keep pure state, and after it is just a breaking coherence by using measurement. But I can see his work is about that is more likely to more related to the unraveling method in the quantum thermodynamics. So I think this is quite different between the measurement-induced phase transition and this quantum trajectory work.
But they connect to each other. I'm going to tell you why. Because if you keep measuring your system, you can also understand this as a non-unitary. So in some limit, you can even write a master equation type of evolution for your system in some limit, if obviously you ignore the results of your measurements. So it's in that sense, it's similar. Okay, it's a slightly different approach. Okay, but you can still derive a kind of master equation because measurements are non-unitary actions on your system anyway. So, but then obviously to reach an equation that is infinitesimal in time, then you have to do these measurements in a particular way. Okay, but it's the kind of physics in some sense.
Okay, let's keep this discussion after.
Okay.
They try to connect it with like stochastic Schrödinger equations.
Yes.
And sometimes I'm kind of skeptical of that too, if it's actually the same thing, because in the stochastic Schrödinger equation, the unitary part is not random, and the random unitary circuit is kind of an important part of those monitor circuits. So I'm not even convinced if the two scenarios are exactly the same, indeed. But they publish, so.
No, fair enough. But thank you again for the comment. Just a reminder that like in quantum optics, we also know for a long time that actually if you have random unitary operations applied to your system, you also derive a master equation, similar master equation with it. So, okay, it's all you need to do is cost grain time. Okay, you cost grain time and you reach a similar. So I'm not saying that it's immediate to make the map. Sure. I'm just saying that it's essentially the same type of physics.
So I think we can move to the next talk.
Okay, so.
Thanks, Marcel, again. Yeah.
Or just here.
Okay, hear me?
So now our next speaker is Bohan. So he's gonna tell you about quantum battery changing. Okay, thank you, Bohan.
Thanks to the organizers for organizing such nice conference in such beautiful city. The title is a bit different from the one on the program, but it covers the same thing. I'm going to talk about charging quantum batteries, how to amplify the charging process by reservoir engineering. So first I will briefly say what is a quantum battery, then the basic model, and then non-reciprocal charging of quantum batteries, and then reciprocal charging of quantum batteries. My presentation is based on these two works. This one published in PRL a few months ago, and this one is now in peer review. So a charging process. In a charging process, we have a quantum charger and like the classical setting, and a quantum battery with some coherent interaction in between them. And this is the laser field. This F, this is a typo. It should be like epsilon. So by epsilon, I mean this F. And the tuning, this delta is the tuning between the laser field and the charger. And the efficiency of the charging process is usually defined by the energy of the battery divided by the energy of the charger. So the first time that, a quantum battery is any quantum system. It can be a 2-level, 3-level, or any n-level system that you can store energy for future use. As you know, the first time, there are many papers about this, and the first time it was by Robert Alinsky, who invented this field. Maybe it's interesting to know that I'm working in the same institute that he's working, and he said that this paper was a joke. So we're making this joke serious. Okay, so the basic model here I'm talking about is the two harmonic oscillators. One is a charger, the second one is a battery. There will be coherent interaction between them, and a laser field and the charger. And A is the annihilation operator of the charger, and B is the annihilation operator of the battery. Okay, so for an ideal case when there is no dissipation in the process, so I should tune my laser field to the this built-in detuning. This built-in detuning is the detuning that while you're constructing your charging system, built-in detuning is built that you should tune your laser field to this, not to the charger, to get the optimal transfer of energy. So as you see, in this case, if I tune my laser field to the charger energy of the battery, this is how it changes. But if I tune it to the built-in detuning, it arbitrarily increases with time, the energy of the battery. Anyway, in realistic processes, we have dissipations due to interaction with environment. Okay, it can be through the charger, to the battery, in the interaction process. So in this case, the optimal detuning is not anymore the built-in detuning. Okay, so when we have in realistic process, when we have dissipations, then we know that the evolution of the whole system is described by a master equation in this form. So the first two terms are for the coherent interaction and the laser field, and the last two terms are for the local dissipation and the charger and the battery with decay rates kappa I and kappa B. And this is the form of the famous form of this GKLS dissipator. Here in this paper, I'm assuming in this presentation that the environment is in 0 temperature, because I don't want to inject energy by the environment. Okay, so for those who don't know what is ergotropy, here I'm using the figure of merit, ergotropy. If ergotropy is defined in the following: if you have a quantum system prepared in state rho with Hamiltonian H, I apply a unitary and take it to another state rho and with the same Hamiltonian. So the process is cyclic in terms of Hamiltonian. So the unitary that takes the system to a state with the minimum energy defines the ergotropy. So ergotropy is the maximum energy that I can extract in form of work in a cyclic Hamiltonian process. Okay, so for now, I will focus on 0 detuning. So I will assume that my laser field is tuned to the charger. I will tell you why, not now. Anyway, so for when I have dissipations in this paper by Farina and others, they show that energy of the battery, its evolution can be described with this formula. Okay, alpha t and beta t are some time-dependent constant. In long time, they have no contribution. So here I have this zeta, and I have this cooperativity, this C, which is the coherent interaction cooperativity between the charger and the battery, is defined by 4J2, the coherent interaction over kappa A and kappa B. And delta is defined in this form, and kappa A and B is kappa A plus kappa B. See, as you see, energy of the battery goes up and then finally decays to a steady state amount. The blue line is the energy of the battery. The dotted red line is the charger, which goes to 0, and the dashed dotted line is the ergotropy. Okay, since I'm using a Markovian bath, my evolution is Markovian, and the bath is in ground in 0 temperature. if the initial state is ground, which is a coherent state, then the map, it maps this such Markovian dynamic maps coherent state to coherent state. So since I choose my ground state to my initial state to be ground, which is a coherent state, then it maps to a coherent state. So for coherent states, we know that energy and ergotropy are the same. So from now on, I just focus on energy, which is equal to ergotropy. Anyway, okay. So now I am trying to enhance the previous result by Farina by using a shared reservoir. So I add a shared reservoir to this whole system, which is interacting with both simultaneously with decay rates gamma. So in this case, one term is added to my evolution, the evolution of the whole system by this gamma dz. So gamma the decay rate of the common bath with this dissipator. Here Z is defined by this PAA and PBB. A and B are the annihilation operators of the charge and the battery, and PA and PB determine the strength of the coupling to the common bath. So the first question that comes to your mind is, why do I add a shared reservoir while I know that it adds more dissipation to my system? All right. So to answer this, I will expand my dissipator with the common bath. It gives 4 terms, as you see, and the first 2 terms lead to pure dissipations, and the last 2 terms provide energy exchange, and dxy is defined in this form. So to see the energy exchange, I am expanding this gamma dxy, and it produces terms like this. See, and as you see, these terms are similar to the terms that are given by the coherent interaction. So this term provides a dissipative interaction between the 2 systems. So it leads to an energy exchange. So as a result, I can display this shared reservoir effect by 2 terms. One is a pure dissipation and one dissipative interaction. Okay, so from now on, I will have 2 kinds of interaction between the 2 systems. One is the coherent one, and one is the dissipative one, and with 2 kinds of dissipations. So the full evolutions of the system is described in this form. So this is the second moment. For the first moment, there are similar equations, but I haven't written them here. So as you see in here, this is the energy of the charger, and this is for energy of the battery, and this is A dagger B for the interaction. So as you see, I have terms like this, J plus I mu gamma over 2 and J minus I mu gamma over 2. So with different signs. If I choose J to be minus I mu gamma over 2, you see that the charger energy doesn't depend on the battery, but the battery energy depends on the charger. So this means that energy only flows from the charger to the battery with this choice. So we call it non-reciprocal for this choice condition, because energy flows in one direction, which leads to the breaking of the time symmetry as well. So only energy goes in this way. The backward energy is blocked. Okay, so as a result, we see that the energy of the battery under the non-reciprocal condition grows to some steady state. Energy of the battery also, but energy of the battery is much bigger than the charger. And here the efficiency of the charging process, as you see, in steady state, becomes 4 gamma 2 over lambda 2. So to compare it with the conventional charging process, by conventional I mean when we have only coherent interaction with no shared reservoir. As you see, I showed in the first few slides, in the beginning slides, that the energy of the charger in the conventional case, it goes up and then it goes to this steady state. But using non-reciprocal technique, energy of the battery goes up and then it never decays. It stays there because energy doesn't go back to the charger to be dissipated. And the efficiency of the battery, and if we define eta B as the energy of the battery in the non-reciprocal case divided by the energy of the battery in the conventional case, as you see, it can be written in this form. C here is the cooperativity again, and epsilon is psi is defined as in this form. And to see in here, C is always bigger than xi over 2 or smaller than xi over 2. For example, here that we have used, if C is much bigger than 1 or much smaller than 1, then eta BB is equal to 4. Okay. So, for example, in here, if we choose kappa, the dissipation rates to be the same, and then xi would be 1. In the weak coupling regime, while coherent interaction is much bigger than this kappa A and kappa B, cooperativity is always bigger than 1. So in the weak coupling regime, using non-reciprocal condition, we get efficiency 4 times bigger than the conventional charging process. Okay, so now I'm telling you why I first used, I talked about zero detuning. Because when we have non-reciprocal condition, energy flows only in one way from charger to battery. So this means that the battery sees the charger, but the charger doesn't see the battery. And this causes the laser field not to see the whole system. The laser field also only sees the charger, not the battery. So it's best for the laser field to tune itself to the charger. So zero detuning is the best. Okay, but what if I'm outside non-reciprocal regime? Well, what if J is not equal to minus I gamma over 2? Is still shared reservoir beneficial? Okay, if I'm outside the non-reciprocal regime and I calculate my energy evolution in the steady state, they are given by this. Okay, here I have introduced kappa A BB and kappa AB as like interaction that restrict the energy transfer, and this J accounts for the interaction that facilitates energy transfer. So here kappa BB is made of this detuning and this decay rate which leads to dissipation. So for if I don't have the shared reservoir, then the optimal detuning is obtained in this form. We see, as you see, this term is the correction to this built-in detuning due to the interaction with the environment. And if I add the shared reservoir, the optimal detuning in this case is much more complicated with this crazy formula. But as we see, so here this blue, I'm plotting the energy of the battery in both cases, while in the conventional case and in the presence of the shared reservoir. The blue dashed line is for the conventional case, when the laser field is tuned to the optimal detuning, and the solid red line is for the case that I have shared reservoir, and then this green line, this dotted green line is for when I'm tuned to charger. So as you see, using shared reservoir is not giving any advantage. It's even worse, a bit worse. But okay, yet still there is one way to exploit the shared reservoir. The technique is this: what if I replace the coherent interaction completely by the dissipative interaction by the shared reservoir? Okay, so this means that I put the J equal to 0 in the equations of motion. So let's see if it leads to better result. And again, as you see, the blue dashed line again is the energy of the battery in the conventional scenario, and the red solid line is for when I have the reservoir, when I have the shell reservoir. Again, as you see, energy of the battery again is worse, even worse than the previous case, while I had both coherent and dissipative interaction. So this means that I lied to you, that there is another way, but I didn't. There is the way for improving the energy transfer, and it's this. I can, using the shell reservoir, I can engineer my interaction. Since I told you in the beginning that interaction with the common but from the charge is defined by gamma PA, and for the battery is gamma PB. So as you see in here, if I can play with PA and PB, I can engineer the interaction while the energy exchange rate stays intact, which is defined by this gamma. I can decrease gamma B, for example, and increase gamma A, but keeping the energy exchange rate intact. So I can do, this allows me to do some optimization. So I do the optimization this way. If I defining X as PA over P2, then in the formula for the energy of the battery and the charger, I take the derivative with respect to X and putting it to 0. With this X, I get my energy of the battery is optimized, which are given by these formulas. Now you see the formulas are quite different, and the main difference between these two is this. In the energy of the battery, we call it super optimal because it's 2 times optimization. One is for the optimal detuning, one is for the interaction. Kappa B in the denominator of B is here, and here is not outside the parentheses. This means if I take kappa B to 0, if I decrease the local dissipation on the battery, allows me for more and more energy in the battery. Okay, and this is impossible in a conventional scenario. Even if you put kappa B to 0 in conventional scenario, energy of the battery has a maximum. It's saturated. Okay, so here, as you see, this is the result of optimization. Before the optimization, these lines, they were very close to each other. Here, the energy of the battery, energy of the charger, in this case, see the solid black line is for the super optimal case, and this line is for the conventional scenario. As you say, the energy of the charger is decreased, and here energy of the battery before it was close to this blue line, which is for the conventional case, but now after the optimization, the super optimal case, it goes up. So simultaneous energy of the charger goes down, and energy of the battery goes up. Optimization due to the energy engineer reservoir. So as I said, the other thing that gives me this super optimal charging is that it allows me for arbitrary and transfer of energy when I am using the dissipative interaction rather than the conventional, the coherent interaction. The left plot is for when I'm using the conventional scenario without shared reservoir, and here this is for the case when the interaction is dissipative. There is no coherent interaction. As you see, it seems like there is no local dissipation. It allows for arbitrary transfer of energy. But in here, even kappa B is 0, see there is saturation. Okay, so there is another question. Why a charger at all? I can just directly charge my battery. Why do I need to use a charger at all? Okay. So in this paper, they questioned this, and they showed that if I have a conventional setting charging scenario, if I remove the charger, as you see, energy of the battery for 0 detuning, energy of the battery can get to its maximum faster. And if the detuning is non-zero, the results are even better in the direct charging. The blue line is for direct charging, the red line is for the charger-mediated process. So, as you saw that the direct charging beats this case, the conventional charger-mediated charging. So we were worried if it beats also our superoptimal technique. So to see this, we define this. So we define this energy, this delta E coherent, which is the energy of the battery in the direct charge in the optimal case minus the energy of the battery in the direct charging. And here delta E dissipative is for energy of the battery in the superoptimal charging minus the energy of the direct the energy of the battery in the direct charging. And the energy of the battery in the direct charging is given by this equation 31. So we get these formulas, and here we have plotted them. As you see, the blue dashed line is always below zero. This means that the direct charging is always better than the conventional charging, even in when it's optimized. But for the supraoptimal case, we see that when the dissipation rate on the battery is lower than some amount, it beats the direct charging. It's always better than the direct charging. And these are my colleagues, Pavel Mazurek and Pavel Hordetsky and Shabir Barzanjaya. He's in Calgary, and these two are in University of Gdansk. And as an advertisement, we put a paper just yesterday on a weak measurement-based protocol for ergotropy protection in open quantum batteries, because there are not many papers on ergotropy protection of batteries when they are filled. Most of the papers are about charging quantum batteries. There are not many papers on keeping the batteries in charged, like for example, if it's in an excited state, it's important to keep it in the excited state, not because we know that quantum systems decay immediately. So here we try to take care of this issue and come to Gdansk. It's a beautiful city, but not as beautiful as Rio.
Okay, let's thank you. Questions? Okay.
Yeah, a bit in the direction of the why a charger at all. I was also screaming the same question initially, but you partially answered, but still one point. I mean, I would understand more the idea of the charger and so on if the two systems were in some way asymmetric, like a charger that in some sense is much bigger than the other, such that you say, okay, I have a charger that is big and not, let's say, portable. So I arrive there with my smaller battery, I charge, and then I go. But here there are two harmonic oscillators. So I was wondering if you thought a little bit in the direction of taking the two systems not exactly the same, like one many body or something like that is, let's say, not portable, and you arrive with your, and then something. Have you?
Actually, this is a good question. For example, like one of them can be a qubit. You mean like, for example, the battery? Yes, this. Yes. No, up to now we haven't worked on it, but yeah, this is a good question. Thanks.
Hi. So thanks for the talk. Do you have any physical intuition on why your result with the coupled dissipation is better than the direct charging?
Okay, this question, it's been a while I've been thinking about. It's the physics behind this, why dissipative interaction leads to. For now, my intuition is when I have, okay, here, when I have coherent interaction, it's easier for the quanta of energy from the battery to go back to the charger. Okay, that's what we call coherent. So with the same rate that it comes to the battery, it goes back to the charger. But in here, it's when a quanta of energy goes to the battery, it takes a longer way to come back, right? And this is one of my intuition that energy it's more difficult for the energy to go back to the charger to be dissipated. This is one thing, and another thing is this. Here it allows for me for this engineering this interaction. This can be smaller, this can be higher. So when energy goes here, it's less likely to go back.
Yeah, so that prompts me to another question. What is actually the state of the battery? Because like if it's direct coupling, if I directly charge, it's a coherent state again of the ratio between charging and so if I put this extra dissipator, it probably won't be a coherent state.
If this is a good question. If the environment, if the bath is in zero temperature, it is shown by, for example, in Serafini book in this book. Its name is Quantum Continuous Variables. I think they show that when the temperature of the bath is zero, if the initial set is coherent, the final set stays coherent. So since we are starting with ground, and ground is a coherent set, and then the final set is ground, that's why energy and work in this presentation are the same, because the state is coherent. But if the temperature is non-zero, it gets mixed, yes.
Any further questions? So thanks again, Mohan. Now we have the coffee break. today. And now you have the pleasure to have Rosario Fazio. Thank you for coming to the conference. And that's it.
So first of all, I should thank you for being here and all the organizers for the organization and for letting me speak at this conference. So I changed the title. I'm going to talk about something which we are currently working on, and I know very little about. It's about a way to define active particles in the quantum regime. So I don't know if it's a good idea to give this talk, but I'll try. I mean, several years ago, I did something similar, and then we submitted a paper to PRL. And the report was, I saw the draft and it looked nice, but then I had the talk by Fazio and I was not convinced. So, and the paper was rejected. So let's say if you are among the potential referees, please refuse to referee, okay? Okay, so it's about what is active particles. I mean, the field is huge, and as I said, is something I really know very little about. But let's say a large part of this field is about particles that are able, and this is something I took from Wikipedia, they are just taking energies from the surrounding to some external environments and are able to move. Okay, so there's this kind of self-propelling mechanism or other way of using this energy to do something. So I will talk only about self-propulsion. So I will talk about only particles that can move, and this is a non-equilibrium process. So in equilibrium, this is not possible. Somehow you have to break detail balance to achieve this. Now, of course, I mean, besides this, there is a lot of a huge activity in defining active matter, where these particles are gathered together, interacting, and the interaction of active particles give rise to a lot of new phenomena displaying collective behavior, topological phenomena, and so on and so forth. Active matter can be frogs, birds, swimmers, but these swimmers may be made artificially. And this somewhat generated during the last decades a huge interest connecting physics, chemistry, biology, and as you can imagine, the community is very large. So far, essentially as far as I know, all the attention has been devoted to classical systems. And just to give you an idea of, so I was pretty shocked about this, how many papers and works are around. This is a standard diagram in which there are number of papers versus years. No, here there is number of reviews appearing as function of years, and you see you go around something like hundreds reviews per year, okay? So that the community felt the need to have a review on reviews, which is So I mean, I trust that these numbers are correct. This is something I took from the archive. But I thought that really to navigate through reviews, you need a review. It's something new for me. So the best thing I could do is just not read none of this, but okay. So as I said, essentially everything which is around so far is about classical systems, but I mean, it's very natural. I'm not the one who asked this question, so you can ask yourself, is it possible to have active motion in the quantum regime? And there are several questions that you will find, I mean, this community you will find pretty natural. I'm not saying anything really new, but just a list of questions that you may ask in this context. So first of all, I mean, you want to understand what are the minimal or necessary ingredients that you really have to put in to realize active particles in the quantum regime. You want to understand if this is just the theory game or there are possibilities. I will comment on this, but we did not do much. But at least there is a fairly reasonable way to realize this in a synthetic system. Quantum effects may show up in the motion, but also may influence the functionalities of the active particles. And these are two different questions that fall in the same category, but they have different nature. And then you really want to see if there are reasonable way also to probe this quantum behavior. Now, you can also ask something else. You say, why do you want to study this? I have no idea why, if this is useful or not, but we were just interested in this. Of course, if you understand how this single particles should be activated, quantum particles should be activated, then in the same way in which people discuss quantum phase transition or dissipative phase transition, then it is very natural to start looking for collective quantum effects in active matter. So as I said, most of the works that are around are classical. So personally, I only found 4 papers, very recent papers, trying to address these questions. So I apologize if you know some other, but I was unable to find. So essentially, first, there was a kind of a description of active quantum particles connecting to non-emission quantum walks, and you will see that somehow what we do is connected, but you will see in which sense. There were various models of activating, let's say, creating an active particles by just having a quantum particle. This is something which was done here. Quantum particle trapped in a potential, but the center of this potential would just be moving randomly, driven by a classical active particles. There is an interesting connection to quantum synchronization for active particles interacting through non-reciprocal forces. And finally, there is, sorry, I just missed this, couple of papers looking at collective effects in this system. So what we did, and this is something, the thing I would like to present, is something very simple. And we took a different route, which we thought is pretty natural. And I mean, you just convert immediately the idea that you have to exchange energy with the environment and move to the fact that there is a very, a natural connection to quantum heat engine. And so we wanted to define symbol models, pretty generic, but symbol models in which this quantum energy, with quantum heat engine might be combined with what we know about active particles to realize an active quantum particles. Let's say one key point which we thought was, again, pretty natural. I'm not saying anything revolutionary, but which was interesting to observe, that if you just design your active quantum particle in this way, that quantumness entering in the heat to motion conversion will be present at two different levels. It will be present in the motion of the particle itself, but I think very important, it will also be present in the way in which energy is converted. Not only, as we all know very well in quantum heat engines, then fluctuations are relevant. And so you will see that also here, the stochastic nature of this heat to motion conversion will become very important, giving rise to very specific signature in the self-propulsion of the particle. So this was our take. We want to really trying to make connection. And really, probably this is too emphatic, but let's say a very natural way to describe quantum active matter is just to make connection to quantum thermodynamics concept. Okay? So this is a work which I'm currently doing with Ludmila Viotti in postdoc in ICTP, with Alexander, Georg Penner, and Felix von Oppen in Berlin, and Liliana Racea in Bariloche by now. So she just moved from Buenos Aires to Bariloche, and let's say most of the credit should be given to Ludmila and Alexander. So, and we hope to put soon just the preprints on the archive. Okay, so let me describe just the model, and then we will. I will briefly tell you a few properties that come out of this of this picture. So we said an active particle should be something just connected to the environment, so it's very natural to have an open system. So the only thing which we should discuss is so some specific properties of this open system. So of course, I mean, you want that your particle should have some internal degrees of freedom that can have transitions, and those transitions will allow energy exchange with the reservoir, but should also have translational degrees of freedom. So this particle should move and should get some internal excitations. And most important, the internal degrees of freedom that I will call spin, I mean, just to make it simple, should be coupled to the translational degrees of freedom, meaning this particle should have kind of spin orbit coupling at some level. Now, a generic form of this, it's just simple. In simple terms, it's just having an Hamiltonian of a particle. I mean, here we are just considering hopping on a one-dimensional lattice, but I think the fact that it's one dimension, the fact that it's hopping, it's not a continuous, is totally irrelevant for what I'm going to say. Simply that there is a term which describes the internal structure of the system. So S is just labels the discrete levels. And then there is an hopping term. Now, you see that this hopping term is characterized by an hopping matrix element in which during the motion, the spin can be preserved, that is S equal S prime, or can change. And so this is essentially the case in which you have hopping associated with some energy, with some change of the internal state. It's just spin orbit, or you want to call it spin-dependent tunneling, or you want to call it non-abelian gauge fields. Is essentially the key to allow for change in energy to be associated with some properties of the motion. So the picture, I mean, you can imagine it's very simple. I mean, there is nothing mysterious. Let me give you just a specific example of this term. Just imagine that you have two levels for the moment, and your spin orbit coupling is such that if you have a transition up, you move to the left. Well, this is right. I don't know. Okay, it moves that way, and if it goes down, goes in the opposite way. Okay, it's as simple as that. But something very important is that this coupling by itself should not play a role, does not play a role if everything is in equilibrium. If your particle is put in equilibrium with the environment, essentially detail balance will guarantee that the kicks in one direction and in the opposite direction are such that no direct motion is possible. So you need a kind of non-equilibrium, and to make it just the standard thing, just to make, for the sake of this discussion, this non-equilibrium is just imagining that you have two reservoirs kept at two different temperatures. And then you see that the idea is totally trivial. You just have, by means of this imbalance, the rate of kicks that you give in one direction are unbalanced with the rates of kicks in the opposite direction, and therefore particle will move one way or another. So all we are discussing is just this. Then, of course, you can modify the internal structure, the spin orbit coupling. There are several different properties that might depend on the specific model. But so essentially, I'm going to discuss this mechanism. I mean, I just create some non-equilibrium and I push it more in one direction than another. Okay? And then that's why, let me say, I would like to emphasize, then you see that quantum will play a role in the motion of the particle, but in principle, if you have complex energy structure or complex spin orbit coupling, then it may play a role in the energy transfer itself. So essentially, I could stop here, but let me give you just simple example, the simplest example you can imagine, I mean, which contains essentially pretty generic features of this, okay? So the simplest example is just two-level systems. And then, so essentially, I mean, all this epsilon is just putting a magnetic field in a given direction, whatever. And spin orbit, you can write it in this way. This is not the most generic form. Actually, the most generic form is when D itself is a complex vector. I mean, these are details, okay? So once you take this, then you can diagonalize and you have two bends, okay? So, and essentially, the fact that you have two bends will play an important, oh, sorry, I mean, there are two bends and there are some dispersion, okay? Some K dispersion. The particle moves. The velocity is just, I think I will write it, I will write somewhere. The velocity is just related to the derivative of the Hamiltonian with respect to K. Something which will play a role, and then I emphasize here, is that is this rotation matrix, which allows to diagonalize the Hamiltonian, which is K dependent. So this is important for the specific of this model, because so each K mode will have a different quantization axis. So it's not that everything occurs on the same axis, and this is a key ingredient. It is also very important because the velocity depends on K. Okay, so this is true also if you take a band. I mean, you just take the derivative with respect of the dispersion, and this will give a K-dependent velocity. So this is also something which will play an important role. At that point, the thing is pretty trivial. So you can reduce in this K, so you can reduce all the discussion to a 2x2 block for this K modes, and the density matrix is just a standard forms where you have this decoupling to the different reservoirs. Okay. So first of all, the velocity. So as I said, the velocity is just the average velocity is just given by the operator traced over the density matrix, and so this is the shape of that you get. There are small things which depends on the fact that you have two-level system, but for the rest it's pretty generic. So first of all, you see that as a function of T, of the base temperature, you get this shape here, which is essentially, for totally different reason, similar to the shape that Steve was describing when he gave his talk. Essentially, so at low temperature and at high temperature, there is no motion. So at low temperature, because if the temperature is much smaller than the splitting, you don't have enough excitations, and so the particle cannot be activated. On the opposite, at high temperature, the two reservoirs are almost equivalent, and so again, for this reason, there is no way to move the particle. Let me say that there is no reason why the two baths should be thermal. Okay, so you may imagine whatever situation. This is what we consider. For this particular simple case, it's pretty simple to derive an expression for the velocity in the linear response. So here, so you see that the fact that you go away from linear response does not change. So it just changed the values of the coupling, the velocity by itself, but the overall feature is not changed. So if you have two levels, then you have to assume that the coupling to the bath is different. If you don't have this asymmetry, then it does not work. But this is only a features of two-level system. Again, another specific features of this example is that you really need also some direct hopping to have this. If the particle will not move by itself, cannot be activated. But for the rest, I mean, let's say already this very simple example capture all the properties. And if you are interested in a multi-level systems, then of course the details will become much more structured. As I said, the velocity will go to 0 at low temperature. This is essentially the minimum gap between the bands, and this is just just thermal activation, so nothing else. So velocity will go to 0 exponentially. At higher temperature, it will go to 0 smoothly as 1 over T cube. In general, it will be a power law. So I'm not sure if T cube is always, it will be always the case. There are, so you may ask quantum effects, where this quantum effects appear. Then the simplest way to see this, and again, there is no mystery in that. If you look at velocity correlations, so essentially, velocity correlation are related to spin-spin correlation. So essentially, what will happen is that the spins, in each K mode, will have Rabi oscillations, and this Rabi oscillation will show up in the velocity. So just this oscillation that you see in the correlation function is just the Rabi oscillation. Okay. So this is probably the simplest way to see quantum effect in the energy motion conversion. Of course, if you're interested in study the quantum effect in the motion itself, then you may imagine different situations like Aron-Bohm effect or just interference. Let's say these particles for the translational degrees of freedom will show essentially, standard quantum features compatible with the fact that it's still an open system, because its spin degrees of freedom are coupled to some external reservoirs, and this will affect also the orbital degrees of freedom. In addition to the quantum effects, then fluctuation will be large. And now I will use the things that were discussed this morning by Marcelo. So in order to study this stochastic dynamics, what you can do is just to look at quantum trajectories. Now, there is one small observation that I should say. So we imagine that we are able just to monitor the dynamics of the particle only by just saying, yes, one quantum of energy was emitted or absorbed, but we really do not know which is the K mode which was involved in this process. So the dynamics that we have to study is just still, it's not a pure state dynamics. It's just, I mean, the evolution will be that of a mixed state. But the only thing which we distinguish is between no absorption and the fact that some events occur. So, I mean, as Marcelo showed this morning, then first of all, this you can see in every trajectory, the velocity will have this, shapes, just smooth evolutions, which is the fact that this particle will get velocity even if there are no jumps, exactly for those reasons that Marcelo explained this morning. And from time to time, it will jump. And all these curves are different examples of trajectories. I mean, there's not much to discuss. Something which we still need to understand well, but is natural to ask, is to see how the absorption or emission of energy quanta will affect the jumps in the velocity. So as you can imagine, depending on where the energy has been absorbed or emitted, this may have, which K mode, this may have a weak or a strong effect on the jump in the velocity. So let me take first this example here. I mean, these are the 4 different processes. Then you see, let me concentrate only on this. You see that this is a case in which you have 2 flat bands. So essentially means that whatever K mode is involved, the energy jump is of the order of 2 in this unit. But then here you see that the spread in the velocity is pretty large, because this may, so this is related to the fact that different K modes will give different behavior. So if you change picture, but I don't want to discuss details of this, of course, so these are the 4 colors are different process, and you may have bands which have a larger dispersion, so the energy change may be wide, but this may lead to more complex behavior in the velocity jumps. So let's say, to which extent all this, one needs to study in details this or not, is something which still we need to understand, but something which we think is worthwhile to explore is the fact that really fluctuations are huge, and actually this particle will have a kind of very fuzzy motion just because of this. Now, we consider, so far, I consider the case in which only the two east paths, or will those that will lead to some energy exchange are important, but in general, there may be some situations in which also the orbital degrees of freedom will be connected to its path, leading to some momentum relaxation. Now, we study these cases, and so it's getting a bit more complicated. What is interesting to say at this level, what I think is interesting, is that what I told you so far survives as long as there is a kind of separation between time scales, in the sense that when momentum relaxation is much smaller than the rates associated with the exchange of energy with the cold and hot path. If this is not the case, yet the motion is more complicated, but the mechanism survives, simply the details that are modified. Is it possible to realize this in some decent apparatus? So the real answer is, I have no idea, but I think yes, because all the ingredients were already around. I mean, spin orbits has been largely studied in quantum gases, and quantum gases were also used as heat engines. So I suspect that this can be. So don't quote me in my report, in your reports to my paper, okay? Because I'm going to write that yes, it is possible to realize, okay? Okay, so and I think I'm done. So I just describe a symbol model of inactive quantum particles. You can find quantum features at various levels in this energy to motion conversion. There are stochastic dynamics effects which are worth to be explored, and we think that cold atoms are a natural playground to realize those. And thank you for the attention.
Questions? No.
Yeah, more than questions are clarifications to be sure that I understood the main points. So the first one is, so if I understand correctly, for you, an active quantum particle is essentially a particle with some internal degrees of freedom such that the hopping is coupled to a change in the internal part. So it's
so that is able to move by changing its internal structure.
Okay, so it's a, let's say, quite, I don't know if call it standard, but it's not anything exotic. You agree? I mean, it's okay.
No.
Okay.
I
Yeah.
think I saw it at the beginning. I mean,
Yeah. Just to be, and also, can you go to the slide in which you define the model actually?
this one?
No, really the first one. Yes, here. So if I understand correctly, you say that, let's say it's quite important that in non-equilibrium situation, you have a net motion towards the right or toward the left. Now, if I understand this Hamiltonian, since you put the Hermitian conjugate, doesn't give this feature.
No.
You have to do it via dissipation, am I right?
No, right. I mean, the
Yeah.
Hamiltonian by itself does not break.
Exactly. Otherwise, will be
right,
non-Hermitian.
right.
The reason why I ask is because, you know, there is this non-Hermitian skin effect and this stuff, and this looks similar. But no, you are.
Like in the sense you see that if you take Limber, the no jump would be analogous of quantum walk.
Perfect.
I mean,
Okay.
a non-Hermitian walk.
Okay, thanks.
So when you show the connection between the oscillations and the oscillations of the spin populations or spin correlation functions and the velocities, is this also for off-diagonal entries of the density matrix or just populations on the diagonal?
So the fact that these oscillations are for the off-diagonal components, but that's why I mentioned this. It is crucial that the quantization axis, that is the rotation between the original spin and the one that lead to this rate equation, is k-dependent. So you cannot find a situation in which all the quantization axis for all the k-mod is the same, and this will lead to some precession of the spin. So this is just Rabi oscillation. There is nothing more than that.
One more quick anticipating, because you said that there will be a moment in which will be interesting to consider the many-body case. Do you think, let's say, there will be more interesting phenomena in the fermionic or in the bosonic case?
No idea. So there is this, I think that there is this nice paper by Marcus Seil group that actually they write a kind of spin, so they are distinguishable particles, and they also see some collective effect. Now, to be understood, if, let's say, if this collective behavior falls down in the class of dissipative phase transition, there is something more. This I don't know.
So actually, I also have a question. But I mean, I think one of the first experimental realizations of a thermal engine was this flywheel engine, when you have, I think it was an ion,
Yes.
and you have the coupling between the internal degrees of freedom and the movement.
Yes.
And then while you do that, actually is converting energy from the spin degrees of freedom
Right.
to the motion. No, is
But,
this?
but that was, I understood that this
It's just
was
also
needed just to connect hot
Yeah, I think they have
hot
kind
and
of-
cold bath. So this was moving, and then it was coupled sometimes to the hot, sometimes
Yeah.
to the cold. I mean, so
I don't think, I mean, because also at the end, I think it's like the laser system, you have the 3 levels and they are always exciting the one, and then it's almost an autonomous engine also there.
yes.
Yeah,
But
it's kind of similar.
no,
No,
but so what we are saying is that, I mean, there is nothing. So this is another type of engine. So instead of doing work, you just
because
you
also, I mean,
allow motion.
it would be interesting also to connect, because I mean, there is also these many papers of, I mean, nano engines in biology, when you're trying to, I mean, these molecules that they, I mean, they're just movement from the ATP energy conversion, then they have on the muscle. So it would be nice to see if you can relate.
I
Yeah.
totally agree.
Any further questions? Cool. So not, so let's just take Rosario again.
Sure.
Tem mais uma, tem mais duas. Essa meia hora e depois. Okay. So, okay, you have to. Okay, now you have Federico. And okay, so thank you also for being here, and that's it.
Hey everyone, I'm Fede. So I'm a Marie Curie postdoc between ICFO in Barcelona and the Universidad de Buenos Aires. And this will be yet another talk on quantum batteries, although I would like to give it maybe a different flavor and maybe provoke some discussion on possible new directions in the community. Maybe in the spirit of the original works of thermodynamics, because I feel like that thermodynamics is a very successful theory that can be applied from single quantum particle to biological system to cosmology itself, and we have a lot of very powerful mathematical tools to study and characterize the fluctuations of work distribution, but nobody's actually proposing a way of harvesting this work, at least at the quantum level, whereas Carnot or Planck were actually thinking exactly of how to optimize the efficiency of some machines for doing practical tasks using finite resources. So I'm not saying that I solved this problem, but maybe I would like to move the discussion in this direction. How do I change slides? Thanks. So I think there was another slide before. Yes. So these are my collaborators at ICFO. Maybe you know Antonio Sin, who's working a lot on Bell non-locality, but has done a lot of also on thermodynamics. And Beatriz is my PhD student. She's brilliant, and she just started, but you will get to know her. So before, why? Spoiler. It's not working. I'm pressing all parts. I'm pressing all possible. Oh, brilliant. All right. How many PhDs then? Sorry. Okay. So before going directly to so these slides first. I think I confused the slides. So before going directly to quantum batteries, I would like to present more or less the framework of my research. So I want to understand what is the relation of energy and information, and in the context of quantum networks. In particular, my expertise is mostly on quantum optics, or more specifically on bosons. So the language I will use is that of our quantum harmonic oscillators. So I talk about quantum optics because it's more natural language for me, but it can be applied to superconducting circuit or to anything that can be modeled as coupled harmonic oscillator with small anharmonicity. And of course, what links all this, say, umbrella title is quantum correlation. So I think that we explored a lot how quantum correlation can be useful for information processing, and not so much how this can be useful for energy processing. And so this was what motivated this work at the beginning, and I kind of failed in that sense because I will show you, but still we found some interesting results. So what is a quantum network of light? It has a very simple and elegant description in terms of symplectic geometry. We can fully characterize this system using the moment of canonical operators, which is typically in the language of harmonic oscillator, the position and the momentum. In the case of light, we have no position and momentum. This is just the real and imaginary part of the electromagnetic field. And the second moment, which gives rise to the covariance matrix, can fully characterize the noise and the entanglement properties of the systems. And in particular, this can be easily decomposed with the so-called Bloch Messiah or Euler decomposition in this way. And this is just telling us that we can apply a squeezing operation and passive optics, and we have the most general Gaussian state. These Gaussian states are very interesting for many things. First, because they are kind of easy to characterize mathematically and to produce experimentally. We can produce a huge entangled state with deterministic operation. And so that's exactly what we did. We characterized complex networks of this state that can be implemented experimentally, and we show that topology is a fundamental quantity for the resource. So it's the resources to implement these networks do not only depend on the number of edges or the number of nodes, they actually depend on the topology of the state. And we applied this, well, for communication protocols, but also we are recently applying them to study what we were talking about before, measurement-induced phase transition, which is an emergent topic that I find very interesting. So Gaussian states are interesting, but are very limited. Somehow they are infinite dimensional states, but they're very simple on the other hand. They can be fully characterized, as we said, by the first two moments. They have a positive probability distribution, so a normal probability distribution in phase space, but they don't encompass the whole Hilbert space. And this limits them, for example, in the sense that they are efficiently simulable with a classical computer. They do not give rise to any non-classical quantum correlation. And so we want to see what happens when we go to non-Gaussian states. And the simple way to go non-Gaussian, at least in quantum optics, is to apply ladder operators. Ladder operators is like creation or annihilation operator that you can see here. So this one in particular, we call it photon subtraction. You literally subtract a photon from the state, and this creates a negative hole in the Wigner function, and this becomes something that scales very bad and becomes very hard to simulate in a classical computer and to implement in any experiment. So people, sorry for this, don't freak out. When we try to study non-Gaussian states, the typical approach is using a truncation of the Hilbert space. I really don't like this approach because somehow it's destroying the continuous variable flavor of the system. We are transforming a continuous system, an infinite dimensional system, in a finite dimensional system. And infinite dimensional systems have very different properties than finite dimensional ones. So I would like to keep the infinite dimensionality of this system. But then how do we study expressions like this one? So this one is like, I'm trying to compute the expectation value of some observable on a non-Gaussian state. I can decompose the observable in some polynomial of ladder operators. I can always do this, and I can decompose the non-Gaussian system again as a series of ladder operators applied to a Gaussian state. So this is very hard to compute, but it can be simplified using a trick from quantum field theory, which is called Wick theorem, and everything simplifies to basically computing the perfect matching. Perfect matching is just we just put indices on all the ladder operators. So this is a very simple example where I have basically the number operators, which count the number of photons in this system. I just put indices over them, and then try to make pairs of all these indices. This operation seems easy, but scales awfully. It scales as the double factorial of the number of indices. It's a P-sharp problem. It's very hard to do, which is the reason why these systems are hard to compute. This is the reason why boson sampling is supposed to give a quantum advantage, etc. Yet it allows us to perform this computation exactly. So I don't have to put any truncation to the Hilbert space, and I can simulate non-Gaussian dynamics using only the property of the covariance matrix, because at the end of the day, this is all this expression reduces to computing sum of product of two-body correlators, which is all encoded in the covariance matrix of the system. So before going to batteries, I want to show you how we can apply this for variational algorithms. because it's kind of pedagogic, and also because today this article was published, so I use this opportunity. So we want to use this for performing quantum simulation, which is what originally initiated the field of quantum information. Yet in what everybody's doing, for example, to study complex theories as quantum field theory, is we have an infinite dimensional theory, and we want to simulate it, say, with superconducting system, which is an infinite dimensional system. What do? We assume that the superconducting system is a qubit. So we just put a cutoff to the Hilbert space. We assume that the quantum field theory has a cutoff. So we simulate a cutoff theory with a cutoff system. And okay, we get something. We can get interesting results. But do we need to do that? I say that in certain cases, no, and that we can get an advantage if we don't do this. So this is what we proposed. So we have a variational quantum eigensolver. So something that we have basically a part that we can optimize that is only composed of Gaussian operations, that is parameterized in a way that we can easily optimize in an experimental setting. We have some non-Gaussian operations. Then we measure the system, the quadrature of the system, which can be directly mapped in the original. For example, if it's a field theory, these are literally the field that we are measuring. And from this, if we want to minimize, for example, the Hamiltonian of this system, we try to minimize the mean value of the Hamiltonian we're observing. We update the parameters with some classical algorithm. We proceed until we find, hopefully, probably a local minima. But yeah. So we applied this first to a many-body system, in particular, Bose-Hubbard model. And here we see that in certain cases, the continuous variable optimizer gives a lower ground state energy than the exact diagonalization, showing that using continuous variables can be more precise somehow, can give more effective results. We try to apply this to quantum field theory, in particular Young-Mills theory. It was not so successful because the algorithm was not expressive enough. So we generalized this by stacking different layers of the variational system and to create some sort of quantum neural network. And we are trying to study this right now. So to go fast, this is what we've done. We proposed a new variational platform that is experimentally available, at least in the quantum optics sense. And we would like to study barren plateau, simulating quantum chemistry, and measurement-induced phase transition. If I didn't say it before, I like measurement-induced phase transition. But now we want to talk about thermodynamics. So energy processing, quantum batteries, finally. So, of course, the motivation, again, is we want to see whether information is actually physical, whether quantum correlations can have an influence in processing the thermodynamic quantities in a more efficient way. I've done some work on this, but I didn't put the identifiers because I have like 10 papers on the archive, so it's gonna be easy to find them if you want. Anyway, batteries are a nice framework to study how we can process energy more efficiently in the quantum setting. And the first relevant work is this by Bender, Felix, powerful charging of quantum batteries, where they show that we can charge batteries in a more powerful way using entangling operations. But then we might wonder, why do we care about power in this setting? I mean, what are we going to charge with these batteries? Your phone? Not really, because like the energy content of this system is ridiculous, and the amount of energy we have to spend to prepare this system and manipulate them is huge. So I think it's super interesting from a fundamental point of view. But from an application point of view, not really. Like, we will not use them for application. And I think this is maybe one of the reasons why industry is not so interested in quantum thermodynamics. No, everybody's trying to build the quantum computers as if we need faster computation. No, but I think we need more efficient machine with less resources right now, and nobody's investing in this. But I guess it's also because we, as a community, we didn't provide useful applications yet. So this is my first work on quantum batteries in the Gaussian regime, so on bosonic batteries. And I was still studying power and efficiency of this battery. I'd done this with Mauro. And at some point, I asked him, do you think these things will be useful eventually? And he literally told me, no. He said, I think that if there is any advantage in quantum, it's on the precision. And I remained with that idea. And I went through, and we showed that in the Gaussian regime, there's no advantage, which is interesting because in the quantum computation world, there is no advantage with the Gaussian operation also. So it's a nice connection between information processing and energy processing. And so what I want to propose is this. So maybe, of course, power is also interesting, and it's kind of complementary to precision. There are some works that show that you cannot optimize precision and power at the same time. And so here we want to focus on the precision, in particular on the signal-to-noise ratio of charging a battery. And this is naturally linked to Glauber theory of optical coherence. Why? Because only quantum light can be subpoissonian. So if I want to go beyond a certain level, certain threshold of the signal-to-noise ratio, I need to use, at the very least, squeezing, which is a non-classical resource. But even that, if I only use squeezing, which is, again, a Gaussian operation, I'm limited in some sense. And to go beyond, I have to use non-Gaussian operation. This is this Hamiltonian, which is the harmonic oscillator. No, the harmonic oscillator Hamiltonian has a very nice physical interpretation because this is the heat current, the electric current that is generated in a photodiode if you shine it with light. So I can measure this, and it produces electric current with exactly the fluctuation, the signal-to-noise ratio that will show you. And so in principle, we could use it as a charger to actually produce work. So these are the first results that we had in the thesis of Beatrice. This is without displacements, because this is the typical approach at the beginning of Gaussian in the continuous variable community. We don't care about displacement because we only care about the entanglement, and displacement don't produce entanglement. Yet it's not a fair comparison because if we use displacements, we can actually increase the signal-to-noise ratio to infinity. I can increase the energy of the system without increasing the changing the fluctuation, and so I can have unbounded signal-to-noise ratio with purely classical operation. However, in a realistic setting, is this useful? What is the application we have in mind? I'm thinking of very small system. I'm thinking of nanotechnologies that I want to charge somehow, and I cannot provide a lot of energy to this system, and I want to provide very precise energy of this system. So I need to impose a cutoff somehow. And if I impose a cutoff, Gaussian operations are necessary. There is a Gaussian limit to how much I can increase the signal-to-noise ratio. And to do this, I will have to perform increasingly complex non-Gaussian operations. And what we see is that in the very large energy and very large temperature, Gaussian states are optimal. But if we go to very small temperature and small energy, which is the regime where we are interested, we require non-Gaussian operation. If you want some intuition, the Fock state has infinite signal-to-noise ratio if at 0 temperature. Then when we increase a bit the temperature, we have to optimize using the variational algorithm we showed before. We have to optimize over the non-Gaussian and the Gaussian operations to find the optimal limit. And then we wanted to see, like, the initial motivation was to see if the entanglement gives an advantage. No, maybe. This is like the signal to noise. It's not really clear. Signal to noise. We just see numerically. What we see is that we observe numerically that when the system is entangled, the signal to noise ratio increases. The problem here is that the entanglement of non-Gaussian state is not well defined, because we have infinite, like all states in the Hilbert space can be entangled. We need to put a cutoff somehow. We either put it in the moment of the quadrature, we either put it in the Fock basis. We are limited, and so I think this is what is limiting this connection. Maybe this thing would be more interesting to study it in a discrete variable settings, but I don't like qubits so much, so I'll leave it to you. So I think this is more or less what I wanted to say. So we show that there is a precision quantum advantage for energy extraction, and that there is a non-Gaussian hierarchy that is called, in the field, is called the stellar rank hierarchy. And this, we are approaching the energetics of quantum correlation. Like, we want to try to find a framework to show if quantum correlations can provide an advantage, or at least to process energy in a more efficient way. I would like the most ambitious part of my project would be to link it with no locality. I don't know if this can be possible, but like with other quantum correlations, we are doing it, for example, with steering. We provide experimental platforms that are already implementable. So I think this is interesting to show new, I don't know, maybe interesting applications. I would like to study fluctuation theorem because like it's again, precision is an important topic in quantum thermodynamics, and it's not very studied in the context of quantum batteries. So I would like to invite you to this workshop we are organizing in Grenoble this year. It's free registration. It's a new community that was created by Alexia that is trying to motivate exactly this. So it's like it will be a sub-community of quantum thermodynamics, trying to see if quantum technologies have a positive or negative impact on energy consumption, on the resources usage. And it unites quantum physicists, quantum information, engineering. I think it's an interesting emerging community. You're all invited. This is all I wanted to talk about. So we show a new framework for the estimation of observable in CV without a cutoff. And we can apply it to many different topics, from quantum simulation to machine learning, thermodynamics, a complex system. And it is photonic hardware inspired. So these things are potentially implementable. 1 minute, I just say one thing more. This framework is useful, in my opinion, when we have many modes and little non-Gaussianity, which is kind of the opposite of what happens with discrete variable numerical simulations, where you, for example, if you use exact diagonalization, if you have a high, like many level qubit system, it's easy to study, but if you have many qubits, it's very hard. So here is the opposite. If I have many modes, it scales polynomially. If I have many levels, if I have many non-Gaussian levels, it's going to be harder. So that's all I wanted to say. Thank you.
Yeah, just maybe a couple of comments. Like, I completely agree. I mean, the early days of this quantum battery thing that we were involved in, Felix, I mean, we never made a claim that we're ever going to do something practical with it. And I think if you really want to work on sort of quantum energy initiative for quantum computing, you should change your field and work on high temperature superconductivity so you can turn off the fridge, because that's like, you know, orders of magnitude greater energy cost than anything that's coming from energy processing of information. So I kind of, that's like my take on it anyway, right? So just to comment on this sort of, there are some examples of situations where work is really stored in, you know, in real systems like experiments. There's like this sort of kind of electromechanical setups, you know, where like Natalia Ares has an experiment where they convert kind of electrical work into mechanical motion. So I mean, I think it's not true that it's just there's less work in it, but there is a bunch of, you know, experiments where people have thought about the conversion. And I also
Natalia Ares.
yeah. I mean, and I also think that, like, you know, it's also connected to this issue that we have generally in thermodynamics. If you read this book by Balian, Microphysics and Macrophysics, he discusses it. When you put lambda of t in a Hamiltonian, there's automatically a classical assumption, even if your system is quantum, right? Because you're assuming that there's some really massive source that's just changing some parameter. Whereas in reality, if it was really an autonomous quantum system, you should really think about the work done autonomously on a quantum system by, say, a scattering particle or whatever. And there are some works done by like Massimiliano, Juan Perando, Sam Jacob and stuff we can talk after. So people are thinking about it. Like,
okay, I will ask you. I was a bit provocative. I know there are some people, I'm not the first one to think about this. Yeah, I see most works on batteries are mostly in that direction. Like we show this is the energy content of these batteries. We have a quantum advantage, which is interesting, but maybe not enough.
Yeah, I have one question about, you said that you didn't do the Barren Plateau study, right?
Not yet.
But in your simulation, you didn't encounter a Barren Plateau. You could optimize well?
In my simulation, so in the simulation we have done, so far we have one layer in the paper we published. We have one layer.
And nevertheless, you could express decently well the ground state.
The ground state
Nice.
of boson of the Bose-Hubbard Hamiltonian, which is like, okay, in a very, we have an advantage in a very specific setting. I think like if we want to go more to more complex state, we don't have it. We are starting to study Barren Plateau, and the situation seems very different than the discrete variable case, but I cannot confirm if the results are correct yet.
And also, I think I didn't understand. You said that by this minimization, you get better than exact diagonalization. What that means? It means that you are diagonalizing a truncation of the Hamiltonian, and you okay. So that is
Exactly. So
initially I was surprised because how can you be better than an exact thing? No, you say I truncate and respect. Okay, yes, got it.
Yeah, I have a question about your variational quantum algorithm, which is, it is very important to show the convergence of your variational quantum algorithm. So, do you have any proof or theorem about the convergence?
About the convergence of the quantum algorithm.
Yeah, right.
So if the algorithm stop somehow.
Yeah, which means is that you have some problem, and so you have to modify your parameter to find the to answer it. Yeah, but this is the CP system. This is the continuous variable system, so it is a different platform. So
no, we don't have a we don't show that this will converge to the exact solution. And I think also in the discrete variable setting, not always you have like most of the cases you don't have this. It's like a heuristic algorithm. We can do this. Let's try to see if it's useful for something. Most cases, no.
Thank you very much. Can you just remind me what's the exact relation, if you have any quantitative relation between the stellar rank and the charging power? Or?
So the stellar rank is basically how many ladder operations I apply to my Gaussian state. Essentially is here. I can give you an analytical expression, but gets increasingly complicated at every layer. What we see is that basically if I want to increase energy, the first photon addition or subtraction will give me one first level, and then I can optimize between the first two energy levels using Gaussian operations, and then I have to increase every time. So
thank you.
This. And this increases the non-Gaussianity and also the signal to noise ratio.
Any further question? So let's thanks again.
Avanti. Ah, ok. No, perché ho visto che è stato tutto. Ah, yeah. Yeah, probably that. Yes.
Okay. Now we come to the last talk of the session. So we're gonna have Dario. Thank you, Dario, for being here.
Yeah, thanks a lot. It's really a pleasure. It's the first time in Rio, so I enjoying the city a lot. So this is based on a work in progress with Francisco, who is currently student in Perimeter. He was a student here in Brazil until a few months ago. Now he moved. Then an old friend, Jeff Murugan from Cape Town, and then myself. A few days ago, I was putting 24 1x. Then I realized that it was too optimistic, so I added 2 because I realized that I cannot stay in November. So let's move. So okay, so this is a little bit an outline of the talk. So I will introduce some preliminaries on quantum batteries. I think there is no need probably, but just to fix the notation, to fix a little bit the language and so on. I will introduce the figure of merit that has been studied, as many people said, a lot, probably too much, which is the charging power. Then I will say a few words about the SYK model. Again, probably I don't need too much, but since the SYK model has been mostly developed in another community, I assume that maybe refreshing a little bit might be useful. And then I will talk a little bit, I will go to the central part of the talk in which I will remind that the SYK quantum batteries provide a charging advantage. And then I will really, the real new part will be here, in which I will say something about an analytical derivation of the charging advantage. So essentially, the entire talk will be to provide an analytical proof, or let's say derivation, I wouldn't call it proof, but an analytical derivation of the charging advantage of the SYK quantum batteries. And then I will, let's say, generalize a little bit by talking about SYK model on graphs, on networks, if you want, using the same terminology used by Federico in the previous talk. So let's remind, so as was reminded by somebody this morning, quantum batteries has been invented by a joke of Robert Alichki that we took too seriously, again. And in this paper, they were essentially introducing the idea, and then the topic flourished a lot, and we are still studying it. So let's, again, remind a little bit the setup that I'm going to use in this dissertation. So I will focus on a system having n over 2 qubits. It will be clear in a moment why I take this funny 1 over 2. And so the total Hilbert space will be simply the tensor product of all of them. So we'll have a dimension like 2 to the power of n over 2. And our battery Hamiltonian will be a very simple Hamiltonian, a single particle Hamiltonian, in which I put, let's say, a constant magnetic field along the x-axis, and that's it. So the battery Hamiltonian is this, and I start my protocol by starting in the ground state. So I put my state in the state minus, 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 and my energy, the initial energy, is, of course, minus n divided by 2. So now the figure of merit is how to charge this battery, and among various protocols, we already heard several, but I will focus on what was probably, okay, now it's starting again. Okay, on what was probably called double quench protocol, something like that, in which very simply at t equal to 0, I turn on another Hamiltonian that doesn't commute with H0, such that my state starts to have a non-trivial evolution. Then at a given time that I call tau, I turn off this Hamiltonian and I go back, such that my energy has a different value that is, by the variational principle, must be higher, or not the variational principle, by quantum mechanics, must be higher, and so I have stored some energy into the battery. So this is what we are going to do. And the figure of merit that we are going to study is the average charging power, which, without too much fantasy, is simply let's say, the subtraction between the energy at the time t, the energy at the time 0, and the division by time. So this is the charging power, the average charging power. And of course, you can extract also, you can define some optimal charging time, which is, for our purposes, simply the moment at which the charging power is maximized. So you maximize over t the charging power, and you define the optimal charging time, tau, and the optimal charging time, the optimal charging power. Okay, so the question that started at the very beginning of the field, I would say, is how large the power can be. And it was introduced by people. Some of them are, at least one is here, the other I don't see. But anyway, to study this idea, they first define a non-quantum protocol that they call the parallel charging, in which essentially they say, okay, let's do something that is completely non-quantum. So I turn on an Hamiltonian that doesn't produce an entanglement, in which all the spins are, let's say, charged separately. And again, it's very easy to realize that in this case, the charging power is simply proportional to the number of qubits. And so they define the idea of quantum charging advantage. They say there is a charging advantage if I can, let's say, engineer another protocol different from the parallel one, which leads to a better scaling of the charging power. So the idea is that you define the charging advantage by dividing the best power that you can have with your protocol with the best power that you can have with the parallel protocol, and you ask if this perhaps is even scaling with n and with some power of n. So these are, let's say, the rules of the game that we are going to play. I'm not going to say a single word about the usefulness or not of this. This is just a theoretical game. We are in a theory conference. It's not my business. I'm not trying to get grants out of that. Okay, so this is a matter of flavor. Federico preferred the other paper. I prefer this one as the first relevant paper on the topic. The authors are more or less the same, so I think nobody feel bad by choosing one or the other. But let's say the very first bound on the best charging advantage that you can have was provided in 2017 in this paper, in which John is here, Lucas was here, I don't see him. But anyway, so they could, let's say, provide a rigorous bound on the best charging power that you can have. And they showed that the best charging power is bounded by essentially two ingredients. One they call K-max, which are the so-called global operations. So an Hamiltonian like this, in which you have a product of all the sigma z in all the possible sites. This is an entangling operation because it couples in a single term an extensive number of qubits. But then in their bound, they couldn't rule out another possible, let's say, ingredient, which were the long-range couplings. So the possibility that one qubit is talking with a qubit far away, but in a, for example, in just a quadratic piece. They couldn't rule out this piece, and this was the best bound. Now, in 2022, I was lucky enough to meet Julian, who is there, who was able essentially to take what they wrote conjecture and make it a proof. So he was able to, because they already have a clear idea that Max was let's say, an uninvited spectator. Nobody wanted there, but the proof was lacking. So what Julian was able to do in that case was to provide a serious proof and show that indeed only global operations matter, and the only source of advantage are the global operation. So far, so good. Now, in between these two papers, there was an extra, let's say, development in which I also contributed, that was to provide an example of a specific model in which an extensive scaling of the advantage was at disposal. And to introduce this model, I need to make a little bit of detour by talking about the SYK model, to talk a little bit what it is, and then I will specify what we did. So the SYK model, is this guy, again, he's super famous. It's funny because he was introduced by Kitaev in a talk. He never published the paper on that, so everybody that wants to cite the SYK model has to cite a talk. I think it's the only case in the history. But anyway, so the model is formulated in terms of n Majorana fermions. Remember, I was saying n over 2 qubits, and the reason why there is this n over 2 is exactly because to map qubits to Majorana, you need a doubling of the number of degrees of freedom, so to say. And so Majorana fermions, for me, are simply quantum operators that satisfy this kind of algebra. So once you have these quantum operators that satisfy this kind of algebra, you can introduce this very, let's say, weird, in some sense, Hamiltonian, in which you realize an all-to-all model that couple together all the Majorana in terms of Q, where Q is, at least in this talk, supposed to be finite. And they are all coupled all together via a Gaussian disorder. By Gaussian disorder, it means that these are simply Gaussian variables extracted from a Gaussian distribution having a variance that scale inversely with n with a power of this kind. The reason being because otherwise the model is not well defined in the thermodynamic limit. Now, our focus today will be only the very simpler case, which is the case in which Q is essentially equal to 2. So our Hamiltonian is simply given by, if you want, let's say a quadratic term. And let's say the all-to-all coupling can be thought as relies on a complete graph. You can think of this procedure if you want. You take a complete graph, so a graph in which every node communicate with every other node. You put each Majorana on each node. So out of this graph, you can extract the adjacency matrix. And out of the adjacency matrix, you randomize it, and you get your Hamiltonian. So there is, if you want, this graph relationship that tells you that an SYK model is essentially a model of fermions living on a graph. So I will focus on this, because all the relevant physics is already here. So given this preliminary, around 2020, I think, we were, let's say, able to show that indeed, if you charge your n over 2 qubits with an SYK Hamiltonian, the one that I showed before, and by doing a numerical exercise, we were able to show that indeed, compared to the parallel in which let's say, the advantage is non-scaling with n, we had a clear and, let's say, robust advantage in the charging power. So, let's say, the advantage is quite clear. Now, a numerical estimation, which was quite brave, but by doing this, we suggested that the scaling of the advantage was suboptimal, was proportional to n to the power 1 over 2. So this was the result. And actually, for example, we had a referee report that for a long time was saying, well, this is just a finite n result. Who knows what happened in the thermodynamic limit? So in a sense, this talk could be interpreted as a reply after 4 years to this referee report. Finally, we are able to provide a derivation in the thermodynamic. It took 4 years. So if the referee is here, listen. So today we will provide an analytical derivation and a funny, I don't know if funny, but okay, something that I like. We will see that the battery charging can be thought as a random walk process on a graph. So we will establish this connection between random walks on graph and the battery charging. Okay, let's start. So first point, we need to put things together. We have qubits on one side, Majorana on the other side. We need some mapping between the two. And we know from our undergrad that this mapping is provided by Jordan Wigner. There are many others, but let's take Jordan Wigner, in which essentially you can map qubits to, if you want, fermions and then to Majorana fermions. It's exactly the same thing. And in particular, by doing the gymnastic, you see that, for example, the Pauli matrix in position J can be written as the product, apart from some proportionality coefficient that I don't care about, but can be written as a product of all the Majoranas from 1 to 2j minus 1. So using, let's say, a terminology quite popular in HepTH community, we can say that a single qubit in position j corresponds to an operator of size 2j minus 1 on the Majorana sense, because you need the product of 2j minus 1 Majorana to build a single qubit. So once we have this, you can retranslate your battery Hamiltonian in terms of Majorana fermions. You could do the opposite as well, but it's much less convenient for the proof. So for the proof, it's much more easy to translate everything in terms of the Majorana. So we do this but it's exactly the same. And so overall, your battery Hamiltonian turned out to be as a summation, an extensive summation of operators with all the possible odd sizes from 1 to n minus 1. So we see, so here I just repeat, I have a summation of operators of different sizes. There are operators with extensive sizes. So there are operators that require an extensive number of Majoranas to be fully reconstructed. This is a crucial, and actually we already understood a few years ago, if you want, as a partial reply to the referee, that this was the first condition for the charging advantage. It was not enough, but was the first condition. So without this property, without these extensive operations, no possibility for quantum advantage. If you want, this is in the Heisenberg picture, is the same phenomenon of the global operations that appear in the theorem by, if you want, by Julian. But it's exactly the same. Okay. Now, extra piece, and then we will go to the real exercise. The SOK Hamiltonian is disordered. So we care about the average power. We don't care about the power that scale very well, but you have to pick a super special realization of the J's. We want something that is average on all the possible realization of the couplings. So what we actually do is to average the charging power over all the realizations of the J's. And it's not hard to realize that psi naught, since this is the ground state of the battery Hamiltonian that is independent on the disorder, doesn't depend on the disorder. So all the disorder average boil down to this term. So if you want, the real challenge is in computing the ensemble average of this crocodile, in which you can do a BCH expansion and can be written as a set of nested commutators doing all the gymnastic, in which our H naught, roughly speaking, is gamma 1 plus gamma 1, gamma 2, gamma 3 plus gamma 1 up to gamma k proportional to n. So this is, let's see how to do. And this is the moment in which Francisco entered into the game and made his contribution. Good. So the main identity that we are going to use is this very simple identity. If we compute the commutator between the SYK Hamiltonian and one Majorana in position I, what we get, again, apart from proportionality constants that we don't care, what we get is a summation over all the possible J's of J, I, J, gamma J. So if you want a single Majorana, after one commutation, gets spread in a superposition involving all the Majoranas, in which all the Majoranas are weighted by this Jij. Now let's repeat, and we get this. We get that the gamma I at the time t can be written as a power series in which I keep iterating with this identity. So it's not hard to realize that here, this quantity is becoming a random walk on the complete graph, because I have an operator that is essentially hopping here and there. And so I'm summing all the possible random walks on the complete graph with coefficients given by J. Now, here, as I said, enters our other ingredient, which is the disorder average. So we don't care about a single realization, but we want to do the disorder average. Again, a little bit of gymnastic. We'll tell you that once you do the disorder average, you are forced to put Ln, the last index, equal to I. So that means that what we are actually computing is a return amplitude. So if you want the amplitude that this Majorana start to hop here and there, and then come back to I. Not only, as was reminded by Federico during his talk, since these are Gaussian variables, we have Wick theorems. So we need to have that each J has exactly one other partner somewhere, and they have to be equal in pairs. Otherwise, the average turns out to be 0. These are two ingredients. The third crucial ingredient is we go to the large n limit. We want to study the dominant contribution when n gets large, to reply to the referee. So what you can show, I think we didn't invent absolutely anything here. You can show that in the large N limit, only the non-crossing pairings survive. So, for example, suppose that I have 4 J's, J this, J this, J this, J this. I can couple in various ways. So, for example, I can choose to say that this J must be equal to this J and this J must be equal to this J. But I could choose also this must be equal to this and this must be equal to this. But in doing that, I create a crossing here. I can show that this makes that this contribution, or better, this contribution is divided by, or is multiplied by a 1 over n factor with respect to this contribution. So when n becomes large, this contribution becomes completely irrelevant by 1 over n expansion. So the only weak contraction that survive in the large N limits are the non-crossing pairings. And if you go in mathematics, you see that non-crossing pairings are one of the many definitions of the Catalan numbers. And so this can be, this random walk can actually be resummed completely, and you will get this quite nice formula in which the time evolution of the singular Majorana can express in terms of the Bessel function of the first kind divided by t. By the way, a posteriori, we realized that this result was in an appendix by a paper of Gross and Rosenhaus. So again, we didn't invent anything. But okay, we rediscovered it, let's say, in another way. Now, however, and this is really new, as far as I know, for sure there will be some Russian paper in which this has been already done, but okay. Our goal is not to compute the time evolution of a single Majorana. We want to compute the evolution of a string of Majoranas in which many Majoranas have to evolve all together. So here, if you want, the big question is, does this product factorize or not? So the question is, this guy can be written as the previous f for a single Majorana to the power of k or not? Here there are two opposite tendencies. On one hand, the model is quadratic, so it's free. So we know that free systems don't interact. So this suggests that we are going towards factorization. On the other hand, Majorana are fermions. So for example, this guy here is not free to hope here because there is already a Majorana. So it's feeling the presence of the other Majoranas. So this is something that is going towards the tendency of not factorize. So again, gymnastic exercise, pen and paper, we realize that at the very end, what happened is a partial factorization. Let's say the naive expression fk to the power of t is not the correct one. What we got is something very close to that, is fk of t over renormalized time, in which the time is not time, but is time times square root of 1 minus k over n. So we see that if k is of order 1 in the large N limit, we get exactly full factorization, which is natural, because if the graph is infinite, the possibility that a Majorana wants to hope in a place where there is another Majorana is very small. So in the large N limit, if k is fixed, factorization should be at work. But if, as it is in the X model, in our battery model, we want to be k scaling with n, this 1 minus k over n become finite in the large N limit, so you have to keep track of this. So far, so good. Now we have really all the ingredients, almost. We can go. So this is the charging power. Is there an advantage? Not clear. I mean, it's not super manageable, this formula. So suppose that I arrive with this formula and I ask you, is this scaling with n or not? I don't know. Not so easy. So what we can do? Well, of course you can, but this doesn't apply to the referee. You can go to finite n, start to plot this and see if there is an advantage or not. But the referee could always say, oh, but this is a finite states effect, so I don't trust. So you need to do something better. So what we did, or better, the idea that Francisco had, was to do apparently a dangerous trick. He said, let's try to do a first order approximation on the single particle part, not notice, this is very important. This is not a first order approximation for the power. It's just a first order approximation for the single particle piece. So in practice, what he did was the following. He said, f to the power of k by this beast can be written as exp k log f, triviality. And then he said, okay, let's now do a first order approximation here at this level. You get this formula. Now this formula is manageable. You can compute. You get this expression. And now here, simply because this guy, to be non-zero, you must have n and t, not the power n t squared, not scaling with n, implies that t, the optimal charging time, must be proportional to 1 over square root of n. Once you plug here, you get this formula. The power is going like n to the power 3 over 2, which means that the advantage is actually n is square root of n, in agreement with the numerics and analytical in the larger limit. So in a sense, this proves the numerical scaling. However, we are physicists, right? So we don't, for example, I guess a mathematician probably here will ask, okay, what is the rest of this truncation? I have no idea. So a mathematician will be not satisfied by this answer because I have absolutely no idea how good, a priori, I have absolutely no idea if this approximation is good or not. So here, the best we can do is, so again, to emphasize, the crucial step was to take a k-point function and do a first order approximation on its single Majorana term. This is a strong approximation, so we should ask, is this approximation valid or not? And if it's valid, why? So at least get an heuristic motivation for the validity of this expression is important. So the first step, we didn't know what to do. We did, okay, let's remind our formulas. So this is exact in the larger limit. Nobody can object. This is so-so in the larger limit. Let's compare these two with some numerical curves, with some curves obtained at finite n by exact diagonalization, and let's see how they work. These are 3 curves. It's not only one. So the blue one that is almost invisible is the exact numerical curve. The orange one that is almost invisible is the exact analytical, this one. The green one is the approximated one. So we got convinced that the approximation is working very well. So now in the last, I'm going fast, so I think you can go to lunch earlier. So, so to finish, I will present the motivation because, I mean, when we saw this excellent, this fantastic agreement, we really wanted to see why such a rude approximation was working so well. So now I'm going to motivate this. Okay, so why the single Majorana first order approximation is so fantastic when it works? Okay, so let's start by thinking what we are actually doing when we do a first order approximation on the single Majorana. Pictorially, what we do is that we take a Majorana that is sitting here, we move in another site, and then Wick theorem forces us to bring back this Majorana to its original position. So by doing the first order approximation, essentially, we are discarding all the contributions coming from these extra paths that might be there, but we discard. Now, let's go to the many Majorana case. So what we are essentially doing is that every Majorana is moved only once and brought back. And on top of that, there is the exclusion principle. So for example, this guy cannot go here if this guy is going here, or this guy cannot go here before this guy is moving. So, but we are not doing anything more than that. We are simply avoiding to move these guys more than once. Why this approximation is so good? The reason is, once again, given by the fact that the relevant operators in the battery Hamiltonian have a number of Majoranas that scales with n. So the approximation works well exactly because we are considering large operators. So if we have an infinite number of Majoranas that are ready to be moved, the chance that by picking at random the Majoranas, we will move a single Majorana twice are suppressed again by 1 over n factors. Once a Majorana is moved, the chance that I pick again randomly this Majorana and then move a second time is overwhelmingly small. So this approximation is working well exactly because of the kind of initial operators that we are considering and that control the charging power. So this ends the reply to the referee after 4 years. So we have the proof and we have an heuristic motivation for this proof. Okay, so let's conclude the talk by saying a generalization. So the lesson that we learn is that in order to have quantum advantage in the SYK setup, you need large operators. So you need operators that can be written as an extensive product of many Majoranas. And you need the ability to move all the Majoranas in a single, at once. How can I say? All the Majoranas must be free to move at least once. So for example, a nearest neighbor chain doesn't have this property because most of the Majorana will sit and will be stuck by the Majoranas outside and they have no freedom to move, and so they cannot enjoy the quantum advantage. So the next question that we addressed is, we know, I also contributed a little bit, but the original idea was from Brian Schwingel. We know that you can deform the SYK model and consider SYK models on various kind of graphs, on sparse graphs. So again, coming back, you remember, the SYK model can be thought as a model of Majoranas living on a complete graph. Now you can say, okay, I remove the complete graph, I put another graph, whatever I like. So the question that we decided to address is when and how we can have quantum advantage in this more general setup. The answer, again, came out by a simple, I would say, graph theory formula. So everything, and I'm right now running the numerics, so I don't have the plots, but trust me that the numerics are as good as the previous one. So we cooked up this quantity, GK, which is essentially a counts how many connections a block of K Majorana has to move the Majoranas outside of the block. And this is the ingredient, like before, that control the power. So the answer is that in order to have a quantum advantage, you need you need this quantity to scale with n. So you need your GK, which counts the number of connections that a block of n, roughly n Majoranas has to escape. You need that this quantity scales with n. If that is the case, you have an advantage. If that is not the case, you don't have an advantage. So I think this is nice because somehow recast the problem of the charging power of an SYK quantum battery in terms of well-defined graph theory questions that you can go to your favorite mathematician in graph theory and ask with a given graph if this satisfies or not this property. So let's conclude. So we finally have an analytical derivation of the quantum charging advantage for SYK quantum batteries. We realize what are the two driving mechanisms for that, the presence of large operators and the ability to fast delocalize these operators. The charging power of SYK has been fully rewritten as a graph theory problem. And in passant, doing this, we also uncovered a partial, if you want, resummation of the perturbative series, which is very suitable for studying large operators in Hoping models. So again, since quantum batteries were a joke and maybe we want to see something else, something that we would like to see in the future is, are there other applications of this particular resummation scheme that we uncovered? I hope there might be applications in physics like thermalization. There might be applications to Anderson localization and MBL and something like that that is probably a bit outside of the scope of the conference, but I still think might be interesting. Okay, I can stop here. Thanks.
Questions?
So I'm not sure I understood what was the original graph you
yeah.
spoke with. So you start with the complete graph?
The complete.
But that, go to the next.
Sorry.
You showed it.
Yeah.
And then you randomize the
No, not the connection, sorry.
Right,
yes,
okay,
the adjacency matrix is just 0 and 1. You throw away once and you put a random number, a Gaussian number.
Okay, and then the power is you were showing that the power goes as n to some alpha.
Yes, and in this particular case, n to the
Sure.
1/2. No, the power n to the 3/2 and the advantage n to the 1/2.
And what is alpha? Alpha is depends on the
Alpha depends on the graph.
Okay.
Alpha
Do you have
depends.
a way, direct way?
Yes, it's I don't exactly remember, but it's a simple function. Sorry, it's a simple function of this scaling for GK. So once you have an understanding of how this graph connect the first n sides with the other, the first n/2 sides with the other n/2 sides, you have an answer for the scaling.
Okay, thanks. And do you think, so you mentioned many body localization and
Yeah,
thermalization.
I would really like.
Do you think that could be relevant for example, these many body quantum scars? I don't know if you ever heard of these things.
My understanding is that for scars, there are better methods because essentially all the times, again, I don't consider myself an expert on scars, but my understanding of scars is that whenever you have a scar, in some way there is an integrability structure that is a little bit broken or is embedded in a more complicated. So I would say there are better tools for that, which is really find the integrability structure behind. So I wouldn't say that, yeah.
Okay, thanks.
Questions?
Giulio.
Okay, thank you very much for your talk. And I think so you have relation between the random walk in the complex graph and the power of the minor fermion, power of SIK model. And that kind of random walk in the complex network is very well studied in the network theory. So I think you can consider that kind of result from them.
Yeah. Let's say, at least for the complete graph, the answer was very simple because in the large N, the resummation of the non-crossing diagrams was simple. So I think we should see how much is known about non-crossing resummation in a generic graph. So yeah, in general, it's not so, I don't know, yeah.
Questions?
Hi, Dario. Thank you for the great talk. I'm just curious to know if there is any quantum material that can realize the SIK model and if you can play around maybe something with graphene. We can
Yes,
whatever.
there are proposals for that, but I know nothing. There are these graphene flakes. Yeah, I heard about it. I heard about it, but I know nothing. There are proposals to realize SYK on flat bands, for example, because flat bands are, I mean, a flat band is a system in which you have an energy band that, as the name say, is flat. So you have an energy band that doesn't depend on K. The energy is fixed. So this kind of, if you want, when you work on flat bands, I know this because I've been in a center very good in that. So I learned things by osmosis. So what I learned is that essentially in a flat band system, you don't have any natural energy scale because the band is flat, so you have no dispersion. And so whatever perturbation you put is immediately non-perturbative. So there are proposals to realize SYK, which is non-perturbative in a flat band setups. I don't know how much feasible they are or not. Yeah. Yes. Yeah, right. But I'm not sure that they have all the other phenomenology that I like, yeah.
More questions?
Hello, Professor. I'm just kind of curious about the delocalization because I didn't really understand where this comes from. I don't know if that's something you want to impose in order to use the Jordan-Wigner, or it's like something natural of the
Oh, okay,
modeling.
good. No, okay, I'm not sure I got fully the question, but you may ask, I mean, you may ask, can I take other Jordan-Wigners, other equivalent mapping in which, where is it? No, yeah, in which I don't have anymore this extensive scaling when I do the Jordan-Wigner? The answer is yes, and the quantum advantage is gone. But again, this should be taken not as a problem, because in a sense, the Jordan-Wigner is part of the protocol in realizing the battery. I mean, suppose that you have a quantum computer, so you have a natural realization of the qubit, but you don't have a natural realization of the Majorana. That is part of the protocol. You have to, let's say, encode the Majorana degrees of freedom into the qubits, and the Jordan-Wigner is part of the protocol. So if you take another Jordan-Wigner realization in which this extensive property is gone, the charging advantage is also gone. So yeah, so it's really part of the protocol at the very end. And this adds to the non-feasibility of this, apart from the academical interest.
From this point of view of a algorithmically implemented Jordan-Wigner, does this map to what Federico was saying, that to have this extensivity has the same flavor of having these global operations?
Yeah, it's
for
exactly
quantum
the same
advantage.
thing. It's exactly the same
But
thing.
this is like this mapping of a quantum advantage to an energetic advantage that Federico was wondering about. Algorithmic advantage to a.
Okay, I'm not so sure of how to reply to the second part. For sure, this is exactly, in this picture, the exact same thing of the entangling operations that you have to do. So it's exactly the same thing, and this makes the entire protocol not feasible, because I mean, already do a gate that encode 3 qubits is already, the Toffoli gate is a problem. I mean, people had hard time to realize the Toffoli gate. Imagine that now I go to an experimentalist and they say, oh, I want a gate that encode n Majorana and qubits at the same time. And so yeah, I mean, I agree that it's not feasible, but this is why I hope that this kind of expansion will have applications in things like Anderson localization and so on, because otherwise I think it's a nice exercise, but we remain an academic curiosity. Instead, you have this partial resummation that might be useful for thermalization or Anderson localization or so on.
But I mean, if I understood correctly, so you could take the results the other way around, no? Saying that actually what he is showing is that to implement a many-body gate, you need a large, I mean, much large amount of energy, no? That scale is.
Oh, yeah, sure. Yeah, absolutely. So, yeah.
Okay.
Yeah.
So I think you end the session. Do you have any information? Okay, so you have the free afternoon. I mean, to organize yourself, you can ask us if you had any tips. Just don't go too wild. We have to be back here tomorrow morning. Okay.